Hello everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through the March 2021. This is for the paper 4.2. It's one of those difficult papers for a lot of A-level students out there. This is the 9701 March 2021 syllabus for the paper 4 variant 2, of which there's only one particular variant for the March session. In line with the recent copyright issues, so hence my new tutorial video doesn't show any question paper or any question at all. So I trust that you know how to access the question paper on your own without me telling you how to, or without me sharing with you how to get those particular papers. Without further ado, let's get started with these kind of tutorials. But before I start, don't forget to support the channel by clicking the button on the bottom right to subscribe to the channel, and follow the channel at ptet.chemistry on Facebook, Instagram and Twitter if you use this platform. And don't forget to share the channel with your friends, chat group, juniors and seniors from school, and various other people who will find the contents of the channel useful in whatever ways they might find it useful. Alright, so despite me not showing the papers with the question paper next to you, which you should have done anyway, instead of just watching me how to do them, the way I'm thinking is still the same. It's just that I might scribble a bit lesser stuff without the question in front of me, but the thinking out loud process is still the same, and you know, I'm still the same person who actually produced the previous tutorial. So let's get started. In this first question, you are asked to complete electronic configuration. If I start from the cobalt atom, so the cobalt atom would have been argon from your periodic table, and then you go to the fourth period, and there's the start of the S block. After potassium and calcium, then you move on to the 3D block, starting from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, and then there will be 3D7. So this is the atom. So cobalt 2 plus is an ion. So that is what the question wants, and they say express it in terms of this argon. So we fill 4s before 3D. We fill 4s before 3D. But we lose 4s before 3D first as well. So we lose from 4s first. So if we have 2 plus, we are losing 2 electrons. So we lost both the electrons, and hence we are left with 3D7. And when you want to go to cobalt 3 plus ion, you lose 1 further. So it's Ar 3D6. So pretty easy start to the question. Part B, so this is a redox question. So it says use the data in the question to predict what happens. So it's a prediction, what happens if any. So they're not saying that a reaction would definitely happen, which is why they ask you to predict if there's any reaction happening, and you got to explain why. So there are 2 bits to it. Is there a reaction? What would you see? And then why is it feasible? Why is it not feasible? So we got to think about electrode cell potential, standard cell potential, by combining 2 half equations together. I think it's worth it if I actually write the half equation down, because it's very hard to explain this without showing you how it works on paper. So this is not exactly showing you the question. These things are available from data booklet. I can also make it available from internet data sources. So you know, these are just data, and these are not the question itself. So I'm pretty sure that is all right. Of course, you know, certain things can't be tampered with, such as this copyright stuff. It's really frustrating, but you know, it is what it is. So I've just got to make full use of the situation and just keep on moving forward. All right, so these are all E0 values, so they are standard. So these are all what they call standard reduction potential. They all show reduction. They all exist as equilibrium. Use the data in the table. Then what's going to happen is the first thing is, if you have aqueous solution of cobalt 3 plus and the cobalt EDTA are left to stand in air, the first scenario is you have aqueous solution of cobalt 3 plus. This is aqueous solution, so this means no EDTA. Okay, no EDTA. So we're going to think about what happens with oxygen and what about without EDTA. So this is cobalt 3 plus. So I'm going to start off by looking at the cobalt 3 plus to cobalt 2 plus. This is actually referring to aqueous. That means without any EDTA, it's just water as a ligand. And I'm going to look at this where this is oxygen going to water there. So what we can see, if I think about that, I'm starting with cobalt 3 plus, so I'm going from cobalt 3 plus to cobalt 2 plus progressively, instead of choosing this, which is starting from cobalt 2 plus to cobalt 0 as a metal. So I'll choose this as my reduction. So this will be your E-ret in terms of explanation. If your E-ret is equal to this cobalt 3 plus, cobalt 2 plus redox equilibrium, so plus 1.82 volt. Then I'm choosing my EOX as the one that involves this oxygen, so whether there'll be whether it will react with the oxygen in the air or not. So then my EOX is that second line, which is 1.23 volt. Then we got to think about, is there a reaction between the two or not? Therefore the E cell is equal to E-ret minus EOX, so that is equal to plus 1.82 volt minus bracket plus 1.23 volt. Press enter your calculator and you will get plus 0.59 volt. Of course, your calculator will not show you the plus when doing physical chemistry, which include this topic called electrochemistry. You got to think about the sign, the value, and the unit as usual. So this is greater than 0, so therefore reaction is feasible and also spontaneous. If it is feasible and spontaneous, then it will happen. But as for whether it will go further or not, so this is minus 0.28, and the reason why it doesn't go further is because if you have to go further, then you have to consider cobalt 2 plus going to cobalt, so that is minus 0.28. This will be your E-ret, and you already stop at cobalt 2 plus there. You already start cobalt 2 plus from cobalt 3 plus, and since your E-ret is more negative than this, it will not go further from cobalt 2 plus to cobalt. It will just stop here at cobalt 2 plus instead of further reduction to cobalt. So I can say no further reduction to cobalt 0, and the reason for it is because if we have to do further reduction, this is your E-ret. Your E-ret at the moment is more negative than this E cell that we have calculated based on starting from cobalt 3 plus to cobalt 2 plus in the presence of the oxygen as well as the water in that aqueous solution without the EDTA. Moving on to the next part, which is an extension of that question. So basically it says in an aqueous solution of cobalt EDTA minus. So we're going to think about the oxidation state of that particular species there. So EDTA comes with EDTA 4 minus. So since it is EDTA 4 minus, the oxidation state of EDTA ion is minus 4. So you can think about the cobalt here being cobalt plus 3, and then minus 4, that gives you minus 1. So here is cobalt plus 3 being reduced to cobalt plus 2, because that EDTA is still minus 4, so plus 2 for the cobalt, minus 4 for 1 EDTA will give you 2 minus overall charge. So this is basically a reduction of cobalt 3 to cobalt 2, but not of the aqueous complex, unlike this one, but it's for the EDTA complex reduction, where you could see that they have different reduction potential, and this could affect the feasibility or how spontaneous the reaction will be. Since we are starting with an aqueous solution of cobalt EDTA, so based on the data, if I am to do this reduction, this is my E-ret. So my E-ret, I'm going to say is plus 0.38 for the cobalt EDTA minus 1 complex. Okay, so based on the data, my E-ret is going to be the cobalt EDTA minus. There is the cobalt 3 plus, and then the cobalt EDTA 2 minus, which is basically the cobalt 2 plus, and that was plus 0.38 volt, and this is less positive. So this is less positive than the EOX for the O2H2O. So remember we had compared with oxidation in the atmosphere. This is oxygen in the atmosphere going to water. So there's plus 1.23 volt. If you want to reduce this, then this is the E-red and this is the partner. So this is the E-ox and this is less positive than this. So the E-ox is plus 1.23 volt. Then your E cell is going to be, in fact, without even calculating, I hope you can see that E-red minus E-ox. If the E-red is less positive than the E-ox, then obviously you're going to end up with something negative, which of course I can show on paper. And if you just pop into your calculator, so 0.38 minus bracket plus 1.23, you're going to get minus 0.85 volt. So this is lesser than 0. And if it's lesser than 0, reaction is not feasible. Reaction is not spontaneous, so we will not see any observable change. So basically it just stays the color of the EDTA, cobalt EDTA minus, so it just stays as this without going to the 2 minus, without going to the cobalt plus 2. What is confusing about this is that the charge there looks as if it's cobalt minus 1, but you got to keep in mind that EDTA is EDTA 4 minus for each ligand, so there's actually cobalt plus 3. There's actually cobalt plus 2, oxidation state, but these are not aqueous complex, these are EDTA complexes, all right? So we are still on question 1, so this is part C now. So they say that we have a cobalt nitrate. We have cobalt nitrate, but let me just recap a little bit of GCSE or IGCSE chemistry, as well as your O-level chemistry. This is the well-known cobalt chloride, which is hydrated with this water of crystallization, and then you heat it. And then you will remove the water of crystallization, and then you remove the water crystallization, you get this other substance. This is the pink color hydrated cobalt chloride, and this is the blue color thing. So basically this is a test for H2O. So similarly, you could use a copper sulfate, which is hydrated, and it will go from blue to white. It's also a test for H2O presence as well, where if you put this blue color thing into here, then you get the pink color. Whereas for the copper to sulfate, CuSO4, if I'm not mistaken, is 5H2O. But I could be mistaken, doesn't matter. I mean, the whole idea is that it could be test for water. This is a white solid, this is a blue solid. So in the presence of water, the white solid will turn blue, telling you that water is present. Anyway, this question is not about either of these. It's about cobalt nitrate, which is also hydrated. So cobalt nitrate, this is a cobalt 2 plus, cobalt 2 nitrate. It's got 6 water of crystallization. So this is red solid. It behaves like hydrated magnesium nitrate. So it behaves like group 2 nitrate. So first of all, the first thing that will happen is the water of crystallization will come off. And the first observation you will see is when heated gently or upon gentle warming, then you will see colorless liquid. You don't see water, you see colorless liquid forms on the upper part of the tube, or you can say condenses on the upper part of the tube that is much cooler, because where you heat it is hot, and then it escapes as water vapor that condenses when it touches or when it gets into contact with the upper part of the tube that is a bit cooler. All right, so obviously we know there is H2O coming off from the formula, but you don't see water, you see a colorless liquid, and that is formed at the upper part of the tube due to condensation. You can use the word condenses if you want to. So there's the water coming off. But then when you heat more strongly, upon much stronger heating, then just like magnesium nitrate, you will see a brown gas, because we will also produce NO2 gas as a result of the formation of NO2 gas, and we'll also produce O2, and we'll also produce the oxide, the divalent oxide, cobalt 2 oxide as a solid. We're going to balance the equation with 2 NO2 coming from 2 NO3. And in terms of the oxygen, here you have 4 oxygen, 5 oxygen. Here you have 6 oxygen, excluding the oxygen here, which is already balanced. I need 6 oxygen. I already have 1, and then 4, I have 5, so I just need 1 more. So I have a half there. This is a gas. This is supposedly a liquid because even though it's as a gas initially, eventually it will condense on the upper part of the tube as liquid. All right. So we see a brown gas. We don't see colorless gas, but of course, when you see the brown gas as a result of heating up a solid, in this case a colored solid, because it's of a transition metal, you will test for oxygen as well. So they didn't ask you to test for it, and you don't see bubbles. You don't see bubbles because this is a solid and this is a liquid that form on the upper part of the tube. You will never see bubbles or effervescence because you do not have a solution to begin with. So be very, very careful of what you're talking about, right? So this is one observation, this is another observation. And in terms of the equation, I've put everything in one go, but in reality, this happened first, and then this happens second, because this is upon gentle warming, this is upon much stronger heating. Question 1, part D, they're asking you on a fixed essay question for 2 marks. So thermal stability of group 2 nitrate. You can still catch some of these fixed essays that I did previously that didn't really show the full question paper, so I have maintained those tutorial videos on my channel as part of A-level concept videos, and hopefully in time I'll add more onto those A-level concept videos without infringing the copyright or showing any questions, but still it will cover my think aloud process that hopefully should help you as well as your friends. Alright, so in terms of this question, so they're asking you why. They are not asking you state the trend, they already give you the trend. So in terms of it, we can say down group 2, there are more filled inner shell. So more and more of the inner shells get occupied, inner shells, or more filled electron shells. So ionic radius of the M2 plus cations increases as the ionic radius increases, but the charges remain the same. The charges remain the same as +2. Size are getting bigger, charge remain the same. So overall charge density. So charge density is charge over volume of the cations decreases. And because it decreases, the cations become less polarizing, or the cations are less polarizing on the anion. The anion in this case is the nitrate anion. So the NO bond, the covalent bond, is less weakened. If it is less weakened, it's not as easy to break, so therefore more difficult to break. If you are more difficult to break the covalent bond, so we can say more stable to heat. If you are more stable to heat, then obviously it requires higher temperature to decompose, and that's why thermal stability of the group 2 carbonate, thermal stability of the group 2 nitrate increases down the group, they become more stable. It's the exact same trend to describe the thermal stability of group 2 carbonates, except that I'll change this to become CO3 2-. So these are the kind of fixed essays that, you know, if you think about the logic of it, you got all the points on a polarizing effect, the thing about charge density, the thing about the covalent bond, whether it's more weakened or less weakened, whether it's easier or harder to decompose, and you have no problem explaining it anytime, any day. In the next question 2, so we have what looks like a Born-Haber cycle. So this is about iron 2 compounds. They're talking about the lattice energy. So they want the lattice energy of FeO. So shown in the diagram, let me just reproduce the diagram. So this diagram is basically E going upward, which is why there are some arrows going upward and there are some arrows going downward. If I'm doing it freehand, I would have done everything in one direction, which you will have seen from some of my other tutorial videos, some of which are still up as a part of the A-level concept tutorial videos. Anyway, so they have got Fe2 plus gas plus or gas plus 2 electrons. As a matter of fact, I think it's probably easier if I actually start from the very bottom and then explain all the way up there. So we do have these Fe2 plus gas plus O2 minus gas, and they go all the way down there to this thing which they have labeled FeO solid. So as you can see, the arrow is going downwards because it's exothermic, and this is actually defined as the lattice energy. This is the lattice energy of FeO because you are forming 1 mole of the ionic solid from its gaseous ion, from its isolated gaseous ions. Forming 1 mole of these require ion 2 plus. One of it require one of the O2 minus gaseous ion as well. Lattice energy is defined in A level, Cambridge International A level, as the energy released when you form the ionic lattice. In other curriculum, they could be defined going the other way, and hence will be endothermic this way. But let's just focus on this since this is the Cambridge International definition as stated in the curriculum. So the other thing that we're going to try and relate them now is going from the elements. The elements that form the iron 2 oxide are iron as a solid as well as oxygen as a gas. There is molecular oxygen, and because it's one oxygen atom and I can only form 1 mole of the substance from its elements, then I need to balance the stoichiometry by using half there. And this is going downward because this is the enthalpy of formation. Well, actually, it doesn't have to go downward, but it so happened that it is going downward. So it's shown like this, which means that it's actually exothermic because it's going downward. All right. And then the next thing they have is the iron solid go to iron gas, but there is no change in the oxygen. So I know these things are given already, but it's important that we could see what's going on there. So there's iron solid going to iron gas. This is the first step that involves the atomization of iron, and there's multiplied by 1 because you're just forming 1 mole of the gaseous atom from its element in its standard states under standard conditions. The next thing that you do is to atomize the oxygen. So atomizing the oxygen, I should really follow the arrow because the arrow is actually going from the energy level to the energy levels like that. So that is actually the iron gas is already iron gaseous atoms, but now I want the oxygen gaseous atom, and this is the atomization of oxygen multiplied by 1. This so happened that this is usually the value that is not given in the exam itself, because they expect the student to be able to relate this to the bond energy, where you are breaking half mole of the covalent bond. So it's half mole of that bond energy as given in the data booklet. This is given, but it's not exactly equal to 1, but it's actually half of it as a result of this equation, where you are forming 1 mole of the gaseous atom, so it's 1 times atomization, but forming 1 mole of the gaseous atom from this gaseous molecule is breaking half mole of the covalent bond. So the relationship there is 1 of the atomization equal to half of the energy of that covalent bond. Is only possible because the definition of the bond energy is for the energy required to break 1 mole of covalent bond into gaseous atoms from gaseous elements. Alright, so basically break 1 mole of the covalent bond into gaseous atoms, everything in the gaseous state. So the next part of that equations goes to Fe gas. In fact, that goes to Fe plus gas plus O gas plus electrons. So this is just the ion undergoing the first ionization energy. So that is your first ionization energy of iron multiplied by 1. And then of course you go further to the second ionization energy in forming the iron 2 plus gas, and then the oxygen gas remains as atoms there because we haven't done anything with it yet, and we will think about it in a little bit. So there's just that thing there, the Fe plus going to Fe2 plus. So this is the second ionization energy of iron, and there's also multiplied by 1 because you're forming 1 mole of the 2 plus cation, 2 plus gaseous cation from 1 mole of the gaseous cation with single charge, singly charged ion or plus 1 ion. And then going from there, so what they have provided you is this thing where there's a line there, and I think that thing was my mistake. Should have probably put it there, and this is going downward like this. And then they say there's Fe2 plus gas, and there's O minus gas, and there's an electron there. So this thing is for the oxygen gaseous atom to gain 1 mole of electrons. So this is actually the first electron affinity of oxygen, and that is multiplied by 1 because it involves 1 mole of gaseous atom gaining 1 mole of electrons to form 1 mole of gaseous ion with single or with a -1 charge. And then it so happened that the second electron affinity, which is basically the O minus going to O2 minus, so that is your second electron affinity of oxygen multiplied by 1, and this is endothermic, but the first one is exothermic because the first one, the atom itself likes to gain electron, but once you become negatively charged, to make it or to force it to gain another electrons, you're moving electrons which are negatively charged to a species with a net negative charge. They're going to repel each other. That's why you need energy. It's endothermic to do second ionization, second electron affinity most of the time compared to the first electron affinity. One of a very common question they are asked. All right. So in terms of everything that's been given, I mean, it's probably quite an easy enough question for the 2 marks because that thing is in front of you. But I've spent a lot of, well, not a lot of time, but some time actually going through all of this expression because you could be asked what each of these actually means, and I've seen those questions come up before, and the whole idea is, would you be able to come up with these on your own? Personally, I really wouldn't draw it in terms of the energy because I like to draw my stuff in a one-way direction, but obviously I know some of them are plus and minus, so I'm better at visualizing things that way. But since this question is given to you like that, so just follow the direction, I guess. So we want the lattice energy, which is this big change here. So we want to go from here to here. So going that way is equal to going this way. So I need to minus this, I need to plus this, and I need to minus this, I need to minus this, minus this, minus this, and plus this. So anything going downward I can plus, anything going upward I need to minus. All right, so going this way is the same as going that way because Hess law says that the enthalpy change of a reaction going this way does not depend on what route you take, so I could be taking this way instead. So going this way is the same as going this way, which is minus. I'm going, hang on, what am I talking about? So I start from here. I go this way. I also start from here, then I'm going opposite, so it's minus this. And then once I'm here, so it's going the other way. Am I correct? Going this way? Sorry, minus this, plus this, minus this, minus this, minus this, minus this, and plus this. All right, okay, so let's get started. So the lattice energy of the FeO is equal to, let's deal with the first one, which is to do with minus the second electron affinity of oxygen. What do we have? We're given the value there as a plus 798. So what I'm going to do is minus and then the plus 798 because I'm going the opposite way, and then this is going the same way. So what I do is I have plus the first electron affinity, which is minus 141, and then I'm going the opposite way, so there's minus this is data given in the not predict table, but the data booklet is 1560, so it's plus 1560, and the first ionization energy is plus 762, and this thing is half times the that thing from the data booklet, the bond energy. All right, so it's half time plus 496, and this thing is already given as plus 416. So where am I? I've done minus this, I have done plus this, now I need to do minus 1560. Now what else do I need to do? I'm going the opposite way, so it's minus, not plus, minus plus 762, and now I'm going the opposite way, so it's minus a half time plus 496, and I'm going the opposite way, so this is minus plus 416, and then I'm going this way, which is in the same direction, so I just need to add, but that value is minus 272. So pop that into your calculator, and I hope it makes sense. You do whatever it takes to make sense for yourself, but when you press calculator with a lot of value like this, there's a high chance that we can potentially make some mistakes here and there. So you need to be very careful, and whatever you do, so try and key them in twice. So I've gotten minus 4197, but let me just double check the calculation. Minus 798 minus 141. I could spot where my mistake was already. So actually I did this as part of my paper 4 tutorial previously, so I'm just looking at my solution for that thing which I got it correct previously, before I had to take down that tutorial video. So what I said just now was we are trying to go this way. So we are starting from here, so we are going this way and then this way, because we are following the route this way, and then we are here, we're going this way. So we need also to go the opposite this, so this is minus the first electron affinity. I had done this incorrectly, so you really need to be careful with all this thing. So I'm going minus, 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 plus. Alright, so everything is minus, and then until the last step, which is plus that one, because I'm going that direction, and then I reach the final SEM destination. Press all that into your calculator, and I will have gotten the same answer which I've gotten. Unfortunately that tutorial video had to be taken down, but so I can be assured that I get exothermic. So there's one good sign that I'm expecting it to be exothermic, as I'm forming the ionic lattice from its gaseous ions with almost no interaction between the isolated gaseous ions. They're so far apart, and I'm forming very strong ionic bonds between the cation and the anion there. I expect to be exothermic. Sign, value and unit for this lattice energy. For the next part of the question, so what do we have? We have question 2, part 2. So we have Wustite. It looks like German word actually. So Fe20 or X. It has both Fe2 plus and Fe3 plus. So what do we have? We have 90% Fe2 plus, 10% Fe3 plus, and they want us to know how many oxygen is there. Alright, so 90% means 90 out of 100 times 20, so there's 9 out of 10 times 20, so there's 18 Fe2 plus. And then this one is just, well, you can either do 10% of it, or you could just take out from 20 iron. Of course 18 are Fe2 plus, that means 2 of them are Fe3 plus. And if you have iron 2 oxide, what you have is iron 2 oxide like that. And if you have 18 Fe2 plus, that means you have 18 like this. And if you have iron 3 plus, you have Fe2O3, because you need 2 iron 3 plus to cancel out the 3 times minus 2, which is minus 6 charges. And you just have one of it like that, because that will give you 2 iron 3 plus. Altogether, if you have a mixture, total up the iron, so you will have 18 iron plus 2 iron, you have 20 iron, and the oxygen is going to give you 1 times 18, which is 18 oxygen, and then you have 3 times 1, which is 3 oxygen. So what you're going to get there is 21. So X equal to 21. That's the number of oxygen you will associate with a formula like this, where you have 20 iron, of which 90% is iron 2 plus, and 10% is iron 3 plus. That's why it's only a 1 mark thing. And I actually got it wrong the first time when I actually did this paper 4. It was thanks to one of the viewers who commented on it. But again, I'm sorry I had to delete all those things, but it had to be done because of certain stuff. Hence, I'm not showing the question paper anymore going forward. Now the next thing, part 3, is all about state and explain. So there are 2 bits to this question. This is about factors affecting lattice energy. So we are asked to compare the lattice energy of FeO versus the lattice energy of calcium oxide. So FeO was what we just did from the Born-Haber cycle. Calcium oxide is a hypothetical thing which you're not asked to calculate, but you're just asked to compare in terms of the factors affecting lattice energy. So the first thing I will be thinking about really is the charges. and then the sizes. All right, so both Fe2 plus and Ca2 plus have the same +2 charge, but we can look from the data booklet. This is iron 2 oxide. From the data booklet, the ionic, not atomic, ionic radius of iron 2 plus is 0.061 nanometer versus the ionic radius of calcium 2 plus, which you can get as well. So from the data booklet, all these data are available. So going forward, I'm pretty sure that you probably know the new syllabus, taking away the data booklet from exams, but it will mean that you probably have the data associated with the question within the question paper itself. They might make it easier, they might make it more difficult, I have no idea. But as long as you have access to data, doesn't matter whether it's data booklet or in the question paper itself, you should be able to use whatever that's been given to you based on what you know. Factors affecting lattice energy, charges, sizes, there's ionic radius, there's ionic charge, then we think about charge density. So what can we say? Iron 2 plus is smaller than calcium 2 plus, therefore charge density, so it's charge over volume, charge density of Fe2 plus is bigger than that of Ca2 plus, therefore iron 2 plus forms stronger ionic bond with O2 minus than with calcium 2 plus. Because you are forming stronger ionic bond, you can be thinking about the lattice energy. So the lattice energy, meaning you're forming the lattice energy FeO, is more exothermic because you're forming stronger ionic bond. So it's more exothermic lattice energy than the lattice energy for calcium oxide. For that particular reason, about same charge but different ionic radius there. Part B, so question 2, part B, what do we have here? We are asked to describe what is disproportionation reaction in the context of the example given. So we know that in the context of example, we cannot just state definition without relating to the example, because they say show how reaction 1. So you have to put it in the context of reaction 1. This is a kind of easier question because you're given an example rather than having to come out on your own. This is called iron 2 oxide. So this is a compound, 0 overall oxidation state for a compound, iron plus 1 oxygen. Oxygen in a compound has oxidation state of -2 most of the time, so there's iron plus 2. This is iron metal as a solid, so it's just elemental oxidation state, which is 0. In a Fe3O4 is actually a mixture. Is a mixture of FeO and Fe2O3. As you could see, there are 3 iron and 4 oxygen. So it's not really just one oxidation state. And this was already mentioned in the early bit of the question. If you have seen it, if you have read it, you would have known what I'm talking about. Fe plus 2, Fe plus 3, because you have actually a mixture of 2 different oxidation state. Oh, actually, it's just mentioned that each formula unit of Fe3O4 contains 1 Fe2 plus and 2 Fe3 plus, like that. So we could see the plus 2 going to that is reduction. The plus 2 going to plus 3, not the plus 2, but going to plus 3, that is oxidation. So we could see in the context of the example, the Fe plus 2 in FeO increases in oxidation number. So I'm trying to explain it now. For 1 mark, I really want to spend the minimum amount of time with it. Increases oxidation number to iron plus 3 in Fe3O4. This is oxidation. And then Fe plus 2 in FeO decreases in oxidation number to Fe0 in Fe. This is reduction. So I have shown the Fe plus 2 in FeO is both oxidized and reduced. So if it is both oxidized and reduced in the same reaction, so this is called disproportionation, and I don't want to repeat the question. So I'm just given 3 lines, and I've just written about 3 lines, which is more than enough, I guess. Whatever you do, avoid writing up marking scheme, because it is not your job as a student to write marking scheme. It's for the examiners actually. All right. So in terms of what happened at the anode, so we know at the cathode, reduction happened at the cathode. Cations go to the cathode, Fe2 plus, Fe3 plus go to the cathode. So at the anode, oxidation happens, and you have the O2 minus. There's the anions that are associated with the iron 2 oxide and iron 3 oxide mixture. So the O2 minus go to O2. Oxidation is loss of electrons. So oxidation is loss of electrons. Reduction is gain of electrons. You lose electrons there. As a matter of fact, you probably start off with electron like this, and I have 2 oxygen atoms, so I need 2 oxygen in front, and this will give me 2 times minus 2, which is minus 4 on the left. This is 0 charge, so I need 4 electrons on the right to balance the charges. Whatever equation you write, balance atom and balance charges. So what do we have next? We have part 3. This is an electrolysis kind of question. Again, I remember getting this one wrong when I actually did it before the marking scheme was released, before the actual video was taken down, and it was actually thanks to thanks to the viewers, you guys. When you spot any mistakes, you will let me know, because that's how you learn, and you're not just watching it for fun. You actually are learning as you go along. All right. Anyway, so they want the maximum mass of iron metal. You start from Fe3O4, which consists of Fe2 plus, and then Fe3 plus, Fe3 plus, like that. And of course you have the O2 minus, O2 minus, O2 minus, O2 minus, like that. We are interested in that. So when you look at it, assume that 1 Fe2 plus and 2 Fe3 plus, one of these and 2 of that, are discharged at the same rate. If they are discharged at the same rate, so I got to think about the reduction happening at cathode, red cat, and then remember that oxidation is loss of electrons, reduction is gain of electrons. So reduction is gaining electron. That plus 2 electrons give me Fe. Electrolysis, reduction happen at cathode, I get Fe from Fe2 plus. If I use a different color one, Fe3 plus electrons giving me Fe, but I have 1 of these and I have 2 of that, so 2 of that plus 2 electrons. That doesn't look right. Hang on. Fe3 plus need 3 electrons to go to Fe, but then I need 2 of that because I have 2 Fe3 plus, so I need 6 of that, and I will need 2 of it. So because what I have is a mixture of both Fe2 plus and Fe3 plus, so what I have then is Fe2 plus 2 Fe3 plus, so I add them together, sum them up, plus 2 Fe3 plus, then I will need 8 electrons because 2 and 6 electrons give me 8 electrons, and I'll get 3 Fe. So that is my final balance equation, and it is essential that I have these based on the information given, that I have 1 Fe2 plus and 2 Fe3 plus. They are discharged at the same rate. 1 of these and 2 of these discharged at the same rate. Once I get my balance equation, I guess the next important thing really is to use the information. So the time is 6 hours. So you need to convert that to seconds because Q go to IT, the T is in seconds. Time by 60 to convert hour to minute, and then times by another 60 to convert that to second. So altogether you time by 3,600. So 6 times 60 times 60, that give me 21,600 seconds. And then Q is equal to IT. So the I is the current is 50 ampere multiplied by time in second. I get let me see with the standard form, 1.08 times 10 to the 6 coulomb. Next up, I need to relate that to a Faraday constant. So 96,500 coulomb is 1 mole of electrons, because the charge for 1 mole of electrons is 96,500 coulomb. If you look from the data booklet, it says 96,500 coulomb per mole of electrons. So in actuality, I have 1.08 times 10 to the 6 coulomb. How many mole of electron is that? That's multiplied by that, divided by 96500. This is the actual mole of electrons. Press that into a calculator and you can get 11.1917. This is mole of electrons. I do not want to run up too early because it's not the last part of the question yet. The last part of the question is calculate the maximum mass of iron metal. I need to look back at my balance equation. This is the iron metal. This is the electrons. I have the mole of electrons. So the mole of iron is to the mole of electrons. I label like this. You have seen this for a long time if you've used my lecture tutorial videos, or you could watch some of my lessons on mole calculations for year 9 mole calculations from IGCSE or O-level chemistry, and you will have seen me doing this all the way from year 9 because it's the same trick again and again. Label things, one thing you want and one thing you have. From the balance equation, 3 Fe to 8 electrons. I have written Fe on top, so on top there is 3. At the bottom I have written electrons, so at the bottom I have 8. And then on the right hand side is equal to what happened in reality. In reality, I have 11.1917 mole of electrons, and on the top is the actual mole of iron. So I will get the actual mole of iron, which is the actual mass of iron, divided by the relative atomic mass, because mass over AR is the actual mole of the iron produced by the electrolysis. Bring that up and hopefully you can see the mathematics easily. If you cannot, then you should do it step by step. In fact, I'm already doing it step by step here. Hopefully that should make sense to you. If you are familiar with the mathematics, you are more than welcome to speed up a little bit and skip one step, but there's something for everyone on my channel. This mass is given in gram because it's in gram per mole, so this thing, the answer will be in gram. So just keep an eye out for that. So 3/8 times 11.1917 times 55.8 55.8 gram, and I got my answer as 234.186. I look at the data provided, 50 amperes. Actually, there isn't much about the data being provided. So I guess what is safe enough is 3 significant figure. If you think about 96,500 coulomb, I could treat this as 3 significant figure. I could also treat it as 5 significant figure, but give or take 1, 2, 3 sig fig. I think that should be alright because I did do the rounding thing before I round it up. So that's in gram. As I said, this is in gram, this is in gram per mole. So this is the 3 significant figure there. So this is still part of question 2, but now part C. So we're talking about lithium-ion rechargeable battery. So lithium-ion rechargeable battery is obviously very, very important these days because everything you use, like laptops, mobile phones, anything with a rechargeable battery typically is one of those lithium polymer battery. So because lithium is one of the lightest metal, being one of the earlier metals, is one of the lighter metals. So lithium batteries are much lighter. So lithium batteries are much lighter. So that's one of the advantages of using lithium. So that's how they make mobile phones that are smaller, well, in fact they can make it bigger, and they can still manage to, you know, shave off or make it a bit lightweight compared to like mobile phone 20 or 30 years ago. One possible advantage, right? So you can say it lasts a long time. Basically, high energy capacity. So these days your phone probably lasts you the whole day, etc. High energy capacity, things like these, high energy density, stuff like that. Okay, so just choose either one really. What do we have? We have a change in cathode. So we want the change in oxidation number at the cathode. So the cathode half equation is Li plus FePO4 plus electrons giving you LiFePO4. So what do we have here? We have the lithium ion, which is lithium plus 1, And then we have phosphate, which is PO4 3 minus. This is an anion. You will have heard of phosphoric acid, one of the reagent from AS level organic chemistry, H3PO4, because this is PO4 3 minus, which means this is Fe3 plus, which means this is iron plus 3. Now what do we have? We also have PO4 3 minus. But then this is a lithium salt, so it's lithium plus, which means therefore plus 1 for the lithium, Fe is unknown, plus 1 times 3 time minus 3, because you have 1 phosphate, the overall compound is uncharged, Fe equal to plus 2 there. So what we have done is the lithium has gone from plus 1 to plus 1, so no change at all, but the iron has gone from plus 3 in this iron 3 phosphate to plus 2 in the final product. Plus 1 plus 2 is plus 3, this is minus 3. Plus 3 minus 3, so you know this is iron 3, it has undergone reduction, gain of electrons, what we talked about earlier. Oxidation is loss of electrons, reduction is gain of electrons. Alright, so the last bit of this question, this 13-mark question, is just asking you to write the equation for the overall reactions that occurs when discharging. So you have half equation and you want the full equation now. So from the half equation, so what do we know from the half equation? Well, you just add up, so I'll show you what happened there. So plus 6 carbon plus lithium plus electrons. I mean, you're just expected to, you know, write your answer down, but since there's no question in front of you, I'm not writing out the question, I'm just writing down the equations which are available even from Wikipedia, I guess. So, you know, you have the question paper to refer to. So this is on the left hand side, this is 1 electrons on the right hand side. As you add them up together, these electrons will cancel because they are equal number of electrons, otherwise you have to do lowest common multiple in order to balance them up. We should probably do the top bit first. So there is LiC6 plus Li plus FePO4, and then they give me 6 carbon plus Li plus LiFePO4. I remember when I did this the first time in the tutorial that I published before the marking scheme, and some people already spotted that, I've cancelled out the electrons, how come I still have the Li plus there? Of course, you can cancel out the Li plus as well. In fact, that's what you should do because it's a spectator ion and you shouldn't include spectator ion in an ionic equation. Although the question didn't specify ionic equations, let's just cancel it out and make ourselves happy because the Li plus are present on both sides of the equation. So I can just cancel that out and move everything closer together and everyone can go home happily. So that's the end of that 13-mark question. So not too bad at all for iron chemistry. So in the next question, number 3, we have this iodate, IO3 minus. They want you, well, in fact, they already given it to you. It's given as IO3 minus. So it's shown as like this. This is iodine plus 5. So iodine oxidation state of which you want to try and find. So you have 3 times minus 2 equal to minus 1 because that overall is an ion. Oxidation state of an ion is the charge of the ion itself. So iodine equal to minus 1 plus 6 because this is minus 6. Move to the other side and you get iodine plus 5. Iodine is less electronegative than oxygen. So when it's bonded to oxygen, it's going to have a positive oxidation state, which is the charge that atom will carry if it is bonded together next to this particular atom, oxygen. As you can see here, the iodine, when this bond breaks, the oxygen is going to take away the electrons. Same here and same here. That's why you get iodine with 5 covalent bond there. And it's an IO3 minus. So according to VSEPR, so meaning to say iodine is in group 7. It has, well, 17. It has 7 valence electrons. It has share 1, 2, 3, 4, 5 electrons. So even though they have drawn it as such, it is actually not 120-degree trigonal planar. It's actually one with 3 bond pair, because you count the sigma bond, 1 sigma, there is 1 sigma here, because what happened there is there's 1 sigma and 1 pi, there's 1 sigma and 1 pi, and there's only 1 sigma there. So 3 bond pair, because there's 3 sigma bond, you only count sigma bond. You cannot have more than 1 sigma bond when you have double or triple bond. So overall what you have is 3 bond pair and 1 lone pair, because the iodine only share 5 out of the 7 valence electron. 3 bond pair, 1 lone pair. This is trigonal pyramidal. This is your AS level case study. This is 107 degree, just like ammonia. So in terms of the electron pair repulsion theory, they're asking you why it has a pyramidal shape. You can think about around the around the iodine atom. I said nitrogen because I was thinking about ammonia. So we can say there are 3 bond pairs and 1 lone pairs. And it's an electron pair repulsion theory. So we need to think about repulsion. So 1 lone pair of electrons, and therefore overall we need to think about the repulsion. The bond pair lone pair, the bond pair lone pair repel more than the bond pair repulsion, bond pair repulsion. Therefore the shape is as such, and the bond angle is 107 degree, and you're just asked to explain the shape, why it is like that. In part B, we are asked to balance an equation. It's between iodine and hot aqueous sodium hydroxide. So the idea of hot is extreme disproportionation. So you learn in a case study with chlorine, where the chlorine 0 will go to chlorine -1, and it will go to a higher oxidation of chlorine +5. This is ClO3 minus, this is Cl minus. These are AS level group 17 chemistry, as well as redox chemistry. This question is asking you on iodine. Similar kind of chemistry applies. They even tell you get sodium iodate 5. There's NaIO3, so plus NaOH. Instead of chloride, I'll get I minus, and there's going to be NaI, this iodine -1, this iodine 0. I will also get NaIO3, which is iodine +5. So what I can do is I can leave a bit more space there, and then I'll get water as well. So what we can see here is that there is changes in oxidation number. 0 to -1 is an increase of +1. If I use a different color, 0 to +5 is an increase of +5. I think I've done something wrong there. There is a decrease from 0 to -1. There is -1 there. So overall, changes in oxidation number must be balanced. Changes in oxidation number must balance in the way that you don't see the electrons on the left or on the right, because the movement of electron must be balanced out in terms of reduction and oxidation. It's an AS level concept. So in order to balance the equation, balance the changes in oxidation number, I multiply that by 5. I multiply that by 1, which means from 0 to +5, there can only be a +5 oxidation number changes. So there's just 1 there. But I need 5 of these in order to give me -5 changes in oxidation number. So it's 5 there. These numbers are now fixed in order to fixate the changes in oxidation number. As we have seen, -5 cancel out +5. 5 sodium and 1 sodium. That means 6 sodium altogether on the right hand side. So 6 NaOH. I've got 5 iodine atom and 1 iodine atom. I've got a total of 6 iodine atoms. These are molecules, so I need 3 I2 because this is balancing equation from your year 9 IGCSE or O-level chemistry. Now you've got 6 hydrogen and there's no hydrogen there. I need 3 3 water molecules to give me 3 times 2, which is 6 hydrogen. So this equation is balanced like that. I have used changes in oxidation number to try and balance these easily from scratch, and that's something you learn in AS level, group 17 or redox chemistry, and it's just a 1 mark thing. So some students like to memorize it, but I never really encourage memorization. If you have to remember something, remember the trick, remember how to get it, so that you never ever forget and you never ever get tricked. In the next question, so part C, so this is question 3. Part C, we have some more electrochemistry question. So it says use the data in the table to show that separate reactions. So they say separate reactions. H2O2, IO3 minus. Separate reaction of H2O2, IO3 minus. So hang on. So it's actually H2O2 and I minus. And I2, sorry, and I2 versus H2O2 and IO3 minus. So 2 separate reactions. So let this be reaction 1 and this be reaction 2. All right, in your answer, give the equation for the reaction of H2O2 with I2. So you also need the equation for this. And we need to show is feasible. Show that it is feasible. So we are given the reduction potential. So we need to work out E cell value, which is E red minus E ox. If I just copy down the equations, which of course is also given in the data booklet, so I am not doing anything that infringes copyright at all. And even if you say these are copyrighted, these are also available online as part of Wikipedia or any other reduction potential sources. So there are no questions shown here whatsoever. I'm assuming you have access to the question paper as a Cambridge learner, so I'm not telling you how to find them. You have to find them yourself, or be a little bit creative. So now we have to think about what is our reactant. Our reactant is H2O2. This is our reactant. In fact, I2 is also our reactant. So this is our reactant. So what happened to the H2O2 is the H2O2 undergo reduction. All of these are what we call reduction potential of the gain electrons. But here the H2O2 is on the other side, so the H2O2 loses electrons. So this is H2O2 losing electrons. This is H2O2 losing electrons. This is H2O2 gaining electrons. So you got to think about H2O2 gaining electrons. So this is reduction, whereas this is oxidation. In a way, I'm saying that it's the H2O2 undergoing reduction, is the H2O2 undergoing reduction here and oxidation here. All right, so we're going to think about reaction with iodine and the reaction with IO3 minus. We've got iodine here, and we've got IO3 minus here. So let's start with reaction 1 first. Reaction 1 starts from iodine. So my iodine, I want to go this way because iodine is my reactant. So I want to go from right to left. So this is oxidation. So meaning to say this is E-ox, reaction 1. And because I'm going this way, the I2 become IO3 minus, the I2 gets, it loses electrons and it gets oxidized. So I need to find a partner where the H2O2 undergo reduction. So this is the E-red reaction 1. So that's what I mark in blue there. So for reaction 1, I can see that E cell is equal to E-red minus E-ox, something you have learned in your syllabus anyway. So it's just about reading this question. So plus 1.77 minus plus 1.19, and you could do that and you will get plus 0.51 volt. So we can see that this thing is greater than 0, therefore feasible, or you can say spontaneous is the same thing. Now for reaction 2, my E cell is also E-red minus E-ox. But then I should use a different color in order to show you what is going on. Let me choose red color. So I'm going to have a look now. For my reaction 2, IO3 minus is my reactant. So I am looking to go from here to here. So I am going this way. So this one will be the I am gaining electrons because this is my reactant. It gains electrons. It gets reduced. So this is my E red, reaction 2. And if this undergoes reduction, then I'm looking for the H2O2 undergoing oxidation. So I can't choose this one because the H2O2 undergo reduction. I have to use this one as my E-ox reaction 2 because here the H2O2 undergoes oxidation since the IO3 minus undergoes reduction. So it's about choosing the right partner. So here this is the E red, so plus 1.19 minus plus 0.68 volt. Press that into your calculator and you will get plus 0.58 volt. So again, we are being asked to show that they are feasible and spontaneous, and we just did the calculations and they are feasible. And the last mark is basically for the equation for reaction 2. So remember that we are trying to do reduction of these, so I can just copy this down, these two equations, and I'll show you how to combine them without going up and down in that way. So what I want is I want this one as my reactant, so this goes this, and this one I will try and move them to the other side so that I can show the oxidation. So that going to that, and hopefully then you can see that this one has 5 electrons, this one has 2 electrons, so times 2 throughout, times 5 throughout. And what you do is you just add them up together. That doesn't look right, as in that doesn't look like they're all in one straight line. So what happened then is your final answer will just have, that doesn't look straight as well. I'm trying to make it look straight. What do you have? You have 2IO3 minus plus, you have 6 times 2, which is 12H plus, and then you would have 5H2O2 going to 2I2. What have I done here? Is there a half? Is there a half there? Yep, there's a half there. So there's times 2, so they will give me 1I2 plus 6H2O plus 5 times 1, which is 5O2 plus 10H plus. The 10 electrons on the right cancel the 10 electrons on the left, but then we also have this problem of 12H plus and 10H plus, so I can move the lesser 10H plus to the other side. 12H plus minus 10H plus give me 2H plus, and then I'll erase this one. So this is my final equation. They involve balancing well, you know, using the 2 half equations. So that will just be my last 1 mark. On to the next part of this question. So this is part C2. So they just want the decomposition of hydrogen peroxide into H2O and O2, and this is catalyzed by acidified IO3 minus. It said the overall equation, the, so meaning there's only one equation that they want. So basically it's catalyzed by IO3 minus, so you don't see IO3 minus on the left or on the right. And of course I need to balance my equation. I have 2 of that and 2 of that. 4 hydrogen, 2 times 2, 2 times 2. 2 times 1 is 2 oxygen, 2 times 1 is 2 oxygen, 4 oxygen, 2 times 2 is 4 oxygen. If you want to think about how does this reaction comes about, of course you can think about this without actually writing them down. So your reaction 1 is basically 5H2O2 plus 2H plus 2IO3 minus. Of course, we didn't write an equation for the equation 1, but I'm just showing you what is happening here. In a reaction 2, which you did write the equation, so H2O2 give you 2IO3 minus plus 2H plus 4H2O. Actually, did I do a mistake? Let me see. 2IO3 minus plus 2H plus 5H2O2. I think that's all right. So what do we have previously? H2O2 with IO3 minus, H2O2 with I2, H2O2 with IO3 minus, and then this one was H2O2 with I2. So that was all right. So H2O2 with IO3 minus and H2O2 with I2. I might have gotten them the other way around, but anyway, the idea is that you have the H plus and the H plus, and then you also have the what am I saying? The two IO3 minus and the two IO3 minus, and you can combine these two equations together, and you can hopefully see that will come down to 10 H2O2, giving you I also missed out one thing, which is the I2 and the I2. So you can get 10 H2O2 giving you 5 O2 and 10 H2O, which you can divide by 5 throughout, and that will give you 2 H2O2, giving you 1 O2 and 2 H2O. So this equation is exactly the same as that, and this was basically the equation that I wrote down to show the overall equation for that 1 mark. Don't really need this, but this is just to show that, you know, all these things, the IO3 minus is just acting as a catalyst where it undergo a reaction and produce an intermediate, and the intermediate gets converted back to the original form of the catalyst, because catalyst is not used up, it's simply involved in the reaction. The next part of the question is basically on rate of reaction. So given this table of data, so we need to determine the order of reaction. So if we think about it, I think it's best if I scribble some data out, because it's a lot easier with the data in front of us. So I'm not gonna exactly copy down all the units and stuff, which, you know, you have it in front of you. These are just numbers. Which of course I can get from scratch. They're just numbers which, you know, you could interpret it as coming from anywhere. And I am not showing the question paper, just so we are clear. And there's H plus 0.025, 0.050, 0.025, 0.025. And this is rate, initial rate, 1.47 times 10 to the minus 5, 2.94 times 10 to the minus 5. So when facing this kind of question, it's basically the same trick again and again and again. So what do we need to do? When we look at these, we need to decide two sets of things, which one to compare. Alright, so there are 3 reactants here, and you need to determine the order of reaction with respect to each of them. They give you a couple of lines, like 4 lines for each bit of the working, for only a total of 3 marks. So what I'll do usually is I usually say let rate equal to rate constant. The first reactant in the column is H2O2. Let me set as A, IO3 minus to the power of B, and then the H plus concentration to the power of C, where this is the order with respect to these, this is the order with respect to these, and this is the order with respect to these. This is a rate constant, and we gotta determine the order of reaction now. Alright, so if I want the order with respect to H2O2, if I want to do this one first, then I need to find something where the IO3 minus and the H plus concentration is constant, basically the same. And I could see that, which one should I choose? I should choose 3 and 4, because hopefully you can see that, you know, that thing there is where both the IO3 minus and the H plus are the same, and I'm changing the H2O2, so that's increasing from here to here. It's increasing by a factor around 1.5, and what happened to the rate here? Alright, to put it into words, okay, so when you explain it, the order with respect to H2O2, this is what we will write down. Compare experiment 3 and 4, when the IO3 minus, which is the second column above, and also H plus, which is the not really the third column, but, you know, the third one for the concentration. This is the H2O2, IO3 minus and H plus, when the IO3 minus and H plus concentration are constant. Okay, and rate 4 over rate 3. I follow my rate equation and follow from the table. On top I put rate 4, which is the higher value. So, you know, just sub in the thing and try to maintain the bookkeeping, and hopefully it should be clear to you in a little bit. So there's from the table, and then I'm gonna put in this thing. Basically what happened there is that you have K, and then you fill in the entry for rate 4, which is this thing. So it's hang on. So the concentration is 0.150 to the power of A, and then there is 0.140 to the power of B and 0.025 to the power of C. I wouldn't really write it out for all of them. I just want to write the first one so they can see what is going on. So it looks like we have 3 unknowns at the moment, A, B, and C. But hopefully you can see why we chose to compare experiment 3 and 4 for this reason, that this and these are exactly the same, irrespective of what B is, because they are exactly the same, and these are exactly the same, so they will get cancelled out, and I don't need to concern myself about that. When you write these equations, the red constant also cancel out. In the end, we are just left with, we're just left with one thing, which we need to solve for. So you put that into your calculator, you get 1.5, and then hopefully you can see that 0.150 over 0.100, A is like 0.150 over 0.100, put all the whole thing to the power of A, and they give you 1.5 to the power of A. Therefore, A is to the power of 1, all right? So this one tells us it is first order with respect to the concentration of H2O2, the only thing that is changing, all right? There's another way of saying this is that when you look at this table, you can say when these things are constant and this increase by a factor of 1.5, where you do this divided by this, and then you will see that this also increases by a factor of 1.5. So therefore, this is first order with respect to the one that you are changing. That way also works. It's the exact same thing as putting it into mathematical terms and explaining it like this. So there are more than one way of getting to the same answer. It's just really up to you, all right? So the next thing is, we gotta get the order with respect to IO3 minus. So we want the IO3 minus to change. So you cannot compare 1 and 2 because, you know, these things are not changing. I want the H2O2 and H plus to be constant. So hopefully you can see that I have to compare experiment 1 as well as experiment 3, because here, this and, is it 1 and 3? I can't really do that, can I? Let's see, I want this one to change. I want the other two to be constant. So this 2 and 3 is the only one where this is constant, and this is also changing. So this is not good at all. So perhaps I have no choice whatsoever. So I want this one to be constant, but I can't choose it. But the only best thing is when these things are changing, but these things are constant. I can see that 1 and 3 is when these are constant. This one are changing when this one are changing. But I already know the order of reaction with respect to this, which was my first answer. First order with respect to H2O2. So I think I have to compare 1 and 3. Or I cannot compare 3 and 4 because this is not changing. I cannot compare 1 and 2 because this is not changing. I can compare 1 and 3 where these things are not changing. I can compare 1 and 4 where these things are not changing, but these things are changing, and even these things are changing. I can work it out based on this. So 1 and 3 or 1 and 4 would have been okay. So if I just say compare experiment 1 and 3, all right, when the H plus concentration is constant, so you can have a look at your own question paper, which of course you don't just listen to my tutorial, you actually practice your actual work, and that is the only best way to learn. So follow your own data in the table. So there's 5.88 times 10 to the minus 5 over 1.47 times 10 to the minus 5 is equal to, I'm going to do the exact same thing, write constant, and then the concentration of H2O2. I know the order because it's first order with respect to H2O2. And the second one is the IO3 minus that is changing. And I don't need to add in the H plus concentration, because if I compare 1 and 3, that is when they are the same. I know they will get cancelled out. So to the power of C, I don't have to key in at all. This is 0.050 at the bottom to the power of 1. This is for N3 for red 1. And then this is 0.0700 to the power of B. The red constant cancel each other out, and I get 4 is equal to this divided by this, I get 2. And then I can combine these two just like I combined this thing for the power A previously. And I will get 0.14 over 0.07, which is 2 to the B. So 4 over 2 equal to 2 to the B. 2 is equal to 2 to the B. B is equal to 1. So again, it is first order with respect to whichever one we are changing. we are changing IO3 minus here. That was our unknown. So it was IO3 minus concentration for the second part. For the third part, you want the order with respect to H plus. You want the order with respect to H plus. To be honest, after having worked out the order with respect to these and these, it doesn't matter which one you compare as long as the H plus is changing. So I cannot compare 3 and 4 where these things are not changing. I cannot compare 1 and 3 where they are not changing, 1 and 4 where they are not changing. I have to compare either 1 and 2, 2 and 3, or 2 and 4. Okay, because I know the order with respect to these and these already. So let's just say I just do, for the sake of it, just compare 1 and 2. So these entries will have been in your table, which, you can do while listening to what I am, talking to you right now. So compare experiment 1 and 2. When IO3 minus is constant, so at least one of them is constant. So I don't have to worry about keying in the value for that. From your table, red 2 over red 1. So you can get 2.94 times 10 to the minus 5. That's the entry for initial rate for red 2. And then that is equal to K for red 2, for reaction 2, for experiment 2. That's to the power of 1. That's the H2O2. And the concentration of IO3 minus is constant. So I don't really have to key it in because I know it will cancel out. So I just key in the concentration of H plus to the power of C. For reaction 1, for experiment 1, so there is 0.0500 to the power of 1, and then 0.025 to the power of C. And hopefully you can see that the K, oops, I don't want that. The K and the K cancel, and that give you 2. This and this give you 2. And the 0.05 over the other one will give you 2 to the power of C. So 2 over 2 equal to 2 to the C. 1 is equal to 2 to the C. Anything to the power of 0 will give you 1. Therefore, we say it is 0 order with respect to the one that was changing, which was H plus, and C is the order of reaction with respect to H plus according to our original algebraic expression to express the red equation. So overall, A is 1, B is 1, and C is 0. So the next bit of the question, which is part 2, is asking you the rate equation. So rate equal to K, the H2O2 to the power of 1, the concentration, and IO3 minus to the power of 1, and the H plus concentration to the power of 0. The next bit of the question is basically using experiment 4. So you have to use experiment 4 data and also rate equation from your part 2, which is just above. So if I follow this equation and I say the rate constant is going to be the rate divided by H2O2 and also IO3 minus. As I said in previous calculation questions, it's best to express what you want in terms of the equation first instead of putting in values, because you'll be saving so much time instead of having to rewrite the numbers before rearranging, and after rearranging you will make more mistake that way. We want the data for experiment 4. So from your table, the rate is 8.82 times 10 to the minus 5. It has a unit given in the table, mole per dm cube per second, divided by 0.150 mole per dm cube and 0.140 mole per dm cube. So at the bottom you have mole per dm cube times mole per dm cube. Both of them are to the power of 1 because first order according to your rate equation. So now looking at the unit, this will usually give you 1 mark. Okay, bookkeeping, so you need to be very careful about the unit. So put the value into your calculator and you get 4.20 times 10 to the minus 3. To be consistent with the number of significant figure, you express it to 3 sig fig, not because it's what you normally do, but because the data in the table you are given were all to 3 sig fig. Well, some of them were to 2 sig fig, but all the rate was given to 3 sig fig, and we have used this data to work out rate constant. So 3 sig fig is not more than 3 sig fig, so it's equally acceptable. Now you have cancelled this mole per dm cube and mole per dm cube. You're going to bring this up there. You cannot just express it as a fraction like this. This will give you mole minus 1. The dm minus 3 will become dm cube, and you have the second minus 1. And just like that, you get 1 mark for the value and 1 mark for the unit. Alright? The next bit of the question, so this is still question 3 and E. Question E is on solubility product. So KSP is an A2 concept. They say the KSP of PbIO3, so lead iodate 5, is going to be 3.69 times 10 to the minus 13 mole cube dm minus 9. So if I look at that, I need to think about writing an equation, which they didn't tell us to. So it's a KSP equilibrium that dissolve to give you the ion. So it's aqueous, and also 2IO3 minus aqueous, because Pb2 plus and 2 of the minus 1 anion. So by looking at that, our KSP is going to be concentration of Pb2 plus raised to the power of 1, because there's 1 in front, times by the concentration of IO3 minus to the power of 2, because there's a 2 in front of the balance equation for the KSP equation. That's part 1. Part 2 is asking you to calculate the solubility in mole per dm cube of the PbIO3. So I'm going to pretend that this equation was actually down there, so that I can use it down here, and there's the equation up there. So if I have that equation there, I can imagine that some of it will dissolve in water, and then I will get a very, very small amount of it that dissolve in water. So I'll have it as mole per dm cube. So the concentration at equilibrium is equal to the solubility at equilibrium. How much of it is soluble in the volume given? How much of it is soluble in the volume given? How much mole of the substance dissolve in 1 dm cube of water? All right. If I get X mole of this that dissolve in 1 dm cube, then the concentration of that is going to be X mole per dm cube. If I have 1 mole per dm cube that dissolve, they are all in the same volume. That's the key thing. They're all in the same volume, because this is an equilibrium. So whatever you get on this side, you get it in here as well, because they are all coming from the same solution, so they all have the same volume. So 1 mole of these will give you 1 mole of these and 2 mole of these in the same volume. So if this is X mole of it that dissolve in 1 dm cube, not very soluble, but some of it are soluble, X mole of it is soluble in 1 dm cube. Therefore, you will get X mole and also 2X mole per dm cube. So your KSP is going to be Pb2 plus IO3 minus square. So this is going to be equal to X square, X to the power of 1, because this is X. And the other one is 2X for the concentration IO3 minus, and square it. And your value given in the question was, let me just write down KSP first. So KSP is equal to 4X cubed. What do we want? We want the solubility of the lead iodate 5. So we want X. We want this thing here, which is X. So X is going to be KSP divided by 4. And then you cube root it. Be careful about use of bracket, because if you make one mistake, and then you will mess up all your calculation. So use bracket very, very carefully. So this is the value given in the question. You divide by 4. Don't forget to cube root and not square root, and you will get an answer, which you should express it to you should express it to 3 significant figure to be appropriate number of significant figure based on the data given in the question. Alright, so that's going to be the solubility. It's got a unit where the unit is already given for you. This question is quite long, so the next part of the question, they want you to work out the entropy change of reaction. So they give you a table. So the reactions has NH4IO3 solid going to half N2 gas plus half O2 gas plus half I2 gas, and also 2H2O liquid. So these are multiples in mole, so we need to be careful. There's no number here, meaning it's just 1. So therefore, the entropy of reaction, or the entropy change for that reaction, is going to be the sum of the entropy of products minus the sum of the entropy of reactants. So it's the sum. So given the table, I would have half half times 192 plus a half times 205 plus a half times 261 for the iodine, and I'll have 2 times 70 because I have 2 H2O. That's going to be the sum of the entropy of the products based on the multiples in the balance equation. I use bracket very carefully because I am worried about making any mistake. As with any calculations, I try to do them stepwise instead of keying in everything to my calculator. And as with any calculations, I need to think about that this is what is shown on my calculator, and they will be wrong because entropy, enthalpy, Gibbs will have sign, value, and also unit. The unit of entropy will not be kilojoule per mole. If you look at the table given, it's already given as joule per Kelvin per mole. So we got to honor that with the sign, value, and unit. Last part of this question is basically saying this reaction is feasible at all temperature. So there are two bits to this thing. So explain using the data in F and also F1. So we need to think about enthalpy as well as entropy and then Gibbs. So delta H is equal to minus 154.6 kilojoule per mole. Is an exothermic reaction. And our entropy change from the previous part of the question is 427 joule per Kelvin per mole. So this is negative given in the question. This is positive, we just calculated it. As delta G equal to delta H minus T times delta S. This is a relationship that's stated in the syllabus, something you must know. When this thing is negative and this thing is positive, and temperature in Kelvin is greater than 0 because you cannot go to negative Kelvin, it's always greater than 0. Greater than 0 times greater than 0 is going to be positive, minus positive will be negative, and this is already negative, so negative and negative, delta G is negative at all temperature, therefore feasible at all temperature. So this is the way to explain it in terms of comparing this being negative and this being negative. T is always positive. So overall, this term will always give delta G as negative for all temperature. That's why it's spontaneous and feasible for all temperature. So that's the end of that 18-mark question. So in the next question, number 4, is about transition metal chemistry. They just want you to start off by defining transition element. So as you would have known directly from the syllabus or among a book of definition that you have been prepared for. So transition elements, transition metal form ions or compounds where you have incompletely filled the subshell. Sorry, I'm just writing a bit slow on my iPad right now. But anyway, so the idea is that transition metals, when they form these compounds or ions, they will have incompletely filled the subshell, and that is when you can call it a transition element or transition metal. So the next part is about what we call the crystal field splitting. So you might not have heard of this term exactly, but crystal field splitting is just the idea that basically explains why you get 3:2 and also 2:3 in an inverted order for octahedral and also tetrahedral complex. So the fact that they do actually ask you tetrahedral complex means that you kind of have to know it, and it's not the first time they've appeared in a Cambridge question actually. So degenerate in the sense that I could draw 5 lines or I could draw 5 boxes. It means they have the same energy. Degenerate meaning the same energy. So this is just basically metal ion which are isolated without ligand. So without any ligand, there's no repulsion, and they are all just of the same energy. Then when you put in some ligand, that means you can have tetrahedral complex where the coordination number would be 4. You get like Ml4, and you can also get octahedral complex where the coordination number is 6, and then you have potentially 6 monodentate ligand, or you can have 3 bidentate ligand, or you can have 2 tridentate ligand, and so on and so forth. So some people like to draw boxes. In fact, the question actually give you in boxes, so perhaps I should really draw the boxes. Let me try and get this right with the boxes. Nope, that doesn't want to be like a boxes. So see if I can get that right. Yep. So 1, 2, 3, 4, 5. So as far as we know, in the presence of ligands, ligands will repel. Ligands contain electron pair that you donate towards the metal center, and whether they are pointing towards the direction of the orbitals that lie along the axis, then they will repel more if they're octahedral, or they will just repel less if they're amongst the two particular orbitals that point in space. They are the dz. Yeah, dx squared y dxy. No, let me get this straight. So we know that you have 3:2. So we know that the one that will get destabilized, a lot more will be the one that repel a lot more. So what you have is you have these 3, and you will have 2 like this, where they are split by this ligand field. This is called octahedral ligand field. As a matter of fact, I really need to draw them just a bit bigger because the octahedral splitting field is actually just a bit bigger than the tetrahedral splitting field. So in most books, they will have shown that both of these are destabilized relative to these because the ligand approaches the orbitals and they will repel. This one will repel slightly more compared to these 3 because these 3 orbitals, they are basically the dxy, dyz, and the dxz. Not that it matters that much in A-level chemistry, but the idea is that they repel more because these are along the axis. They point along the axis, and this one is in space, or what we say through space. I'll show you an example. So for example, if I say dx squared y squared, so this will be y and x like this, and then I will have dx squared y squared. This is along the axis. So this is a dx squared y squared orbital versus let's say a dxy. So dxy orbital would point in space like this. So they are in between. The axis. So when your ligand approaches, your ligand will approach there and your ligand will approach there, and as such they will repel more if the ligand approaches in the octahedral direction, such as this. Then dx squared y squared and dz squared will be destabilized a lot more because they repel a lot more. That's the reason why you get these 2 set of orbitals that point along the axis, repelling more with the electron pair that the ligand bring in as part of the definition of ligand that form dative covalent bond to the metal center. When you form tetrahedral complex, on the other hand, the order is reversed. So you get 2 and you will get 3 like this, and this is the tetrahedral splitting field, which in reality is actually a bit smaller than the octahedral splitting field, but you don't really care that much, at least not for A-level chemistry. I've also done previous tutorials where I actually show the 3 going down and the 2 going up, and the 2 going down and the 3 going up for tetrahedral complex. In reality, it does not really matter, but the idea is that both of these will get destabilized when the ligands approaches the orbitals in that particular direction, in that sense. That's why these are destabilized, and this is destabilized more than this. Of course, electrons will repel, assuming you have electrons in the d orbitals, because incompletely filled d subshell. So it is filled, but it's filled incompletely. So there are electrons in the d orbitals, and then the ligands will bring electrons that will repel with it. For that 1 mark, I was just going beyond whatever is required to try and explain, the idea that why they split 3:2 for octahedral and 2:3 for tetrahedral complex. As a matter of fact, do ask you to sketch the shape of the 2 orbitals. So depending on what they want you to draw there. So they say 1d orbital from the lower energy level. So let me use their axis. So their axis is x, y like this. So y, x, and then that doesn't look so good. Let me see if I can get this right. So there's the z. If I just copy this before I draw anything in, they will save me time later on. So they want from the lower energy level. So lower energy level, and they also specify octahedral. So this is among the three sets here, the dxy, yz, or xz. We're going to draw it in between the space. So this is actually dxy because it cut in between the space x and y. So they are not asking for level, but let me just get this straight. So in between x and y, in between x and y, so that looks like this. This is actually dxy. If you draw in between z and x, there will be dxz and so on and so forth. And you want the higher energy level as shown on the question paper, which of course I'm not showing you here because of certain restrictions. So I'm going to draw the dz square because I already drawn the dxy, which cut the axis there. So just to show you a different flavor, it cuts the z, and there's like a donut ring in between, and this is actually the dz square orbital. You're not being asked to level, but it never hurts to know a bit more than that. On to the next part. This is a slightly weird question because they tell you EDDS for minus. So let me just draw the skeletal formula because it's almost impossible to describe this chemistry without drawing the skeletal formula. So I'm not sure if this actually constitutes copywriting, me copying down the question, whether that constitutes a breach of copyright or not, but I suppose doesn't hurt to try and see whether if they get in touch with me again, then I might have to delete this video again. So let's hope not. I try my best to stay within the copyright issue thing by not doing funny things like sharing links or showing the question paper, etc, etc. This is your classic EDTF4 minus, which is in the syllabus. This is something new which you might not have seen before, but immediately you can see a difference is that the nitrogen there form 3 covalent bonds without any hydrogen, but still has the lone pair there. Of course, they don't show you the lone pair, but as usual, we need to think about the lone pair like this, which is why when you think about the coordination site, there's 1, 2, 3, 4, but we know it's a hexadentate ligand, 5 and 6 because they are lone pair on the nitrogen there. If you think about the EDDS4 minus, what they want you to do specifically in the question is to circle any atom that forms a dative covalent bond. So that bond is a dative covalent bond. That means it's an electron pair donor. So you need to donate a pair of electrons. Should be pretty clear that you have it there. You want to circle each atom. You want to circle the atom. So I want to circle the atom because it's not the carbon that says circle the meaning only one atom. Circle each atom. Sorry, they don't say the, but each atom. So some people will circle this whole group and you're not following the instruction really. Each atom is actually the lone pair on the oxygen that form the dative covalent bond. And it's the lone pair there on the oxygen as well as on the oxygen that has the negative charge in the lone pair that form dative covalent bond. There's lone pair on the nitrogen, and in fact that nitrogen is the atom that will form the dative covalent bond and not the hydrogen, and certainly not the whole group. NH is just the nitrogen. Alright, the next bit is asking you on why the two complexes have different colors. This is basically a fixed essay. If you have caught up with my what I've done on the channel previously, so you have heard of me explaining why this one is. If we look back on the previous question, so we saw that in the absence of ligand, these orbitals are degenerate. They have the same energy, but they do split in the presence of ligand because of electronic repulsion. And when they split, there's an energy gap, and this energy gap means the electrons and the lower energy level can go up to the high energy level. This is called excitation, and that can only happen if they absorb visible light, which is electromagnetic radiation. So they absorb photons from the visible light, and they will be promoted and excited. And having done that, when they relax back, and then they will when they get promoted and excited, they will absorb in the visible light region, and whatever that is being absorbed is not what you see. You see whatever that is not being absorbed by the metal ion as it does all this excitation thing. So what can I say? I can say that the different ligands or ligands on its own result in different delta E splitting. So delta E splitting is the energy gap between the two set of orbital. So energy gap between the two set of orbitals. This question is asking you why the, like both of them are iron 2 plus, iron 3 plus, iron 2, hang on, you have FeEDDS minus. So overall is a -1. Iron you don't know, but each EDDS is -4, just like EDTF4 minus, EDDS4 minus. So each Fe is +3. So this is the iron 3. Each of them is iron 3. One of them is red, one of them is yellow. Obviously the different ligands, EDDS versus EDTA, causes different splitting. And because you have different splitting, then delta E is equal to HF is equal to HC over lambda. This lambda refer to lambda, meaning the wavelength of the visible light being absorbed. So the electrons in the lower energy level absorb visible light in the electromagnetic radiation or in the electromagnetic spectrum. So electronic visible light. I probably don't need to mention electromagnetic, it's just confusing. Visible light of different wavelength. So lambda refer to the wavelength just now. So perhaps I can just write down lambda. So hence different lambda absorbed, since I already defined what lambda is, causes different visible light to pass through. So remember that it is the color or the combination of the color that passes through. Therefore we will see different color to pass through. Therefore we see different complementary color. This is something that will have been mentioned in your classes, as well as in the notes that you make yourself, because this is advanced level chemistry, so you don't just rely on a teacher, but rather you actually make your own notes. It's independent learning, really. So the type of reactions occurring with that aqua complex, and then you substitute with the ligand. So this is very clearly a ligand replacement, or really what I call as ligand substitution reaction. So very clear forward, very clear is just that 1 mark. So I'm pretty sure this was still question 4 if I'm not mistaken, and it is question 4 still, so pretty long question. So 4C part 4. So this is about stability constant. So looking at that equation, so K step is not Kc. K step is about the stability of a complex, whether the complex on the left or on the right of the equilibrium is more stable. We do not include the concentration of water. So first of all, on the right hand side, I have iron, EDDS, bracket, and then minus. This is the charge for the complex. Now I want concentration, so I put another big square bracket. Be very careful about your bookkeeping. That is to the power of 1, because the number in front of the equation is just 1 mole. So what else do I have? I have the iron, H2O6, and then 3 plus. This is the charge outside the complex formula. So another big square bracket to represent concentration, against the power of 1, because from the balance equation, that is 1 mole. This is just how EDDS4 minus is presented in the equation. So it's just concentration of that, again to the power of 1. I do not include water concentration, because water concentration is already taken into account by K step. And if you are doing Kc, if it is Kc from AS chemistry, then you will need to include the water, but not for K step. On to the next part. So we see that the iron EDDS minus, it's a 10 to the 20 versus 10 to the 25 for the EDTA complex. So you have two parts of the question. Predict which one is more stable. So the one with the higher value of K-step is not just the value that you're seeing. So you're given 3.98 times 10 to the 20, but you're also given 1.26 times 10 to the 25. Some students, they will just see the number and they say this is bigger, but this is where your mathematics come into importance. As you could see, this is about, it has got 10 to the 5 bigger than this. So you know, this is very important, much bigger compared to 10 to the 20. So therefore, the bigger the K-step value, this is for FEEDTA minus. So FEEDTA minus is more stable compared to the EDDS complex. And the reason for it is because, well, you know, K-step for iron EDTA minus is higher or bigger. Of course, this is comparison, so you know, I can compare than that, which is the K-step for FEEDDS minus. Whatever you do when you compare something, do not just leave it hanging without completing the sentence. The next bit of the question is basically asking you calculate the equilibrium constant using the K-step value. So if you think about it, okay, let me just give you a shortcut to this. I'm not going to write the whole equations, but you know, plus something something, and then you get the iron EDTA, which is already given in the question, obviously, plus something something something. So we are saying that the EDTA complex is more stable. We are saying that this is more stable, and this is less stable. So the more stable it is means the equilibrium favors that side, and you want Kc. So because this is more stable on the right compared to the left, so you favor this way. If you favor the right hand side, Kc must be bigger than 1. If your answer later on does not come to bigger than 1, you know you have done something wrong. So in terms of Kc, just by using this K-step value, you're gonna gotta think about the ratio, because it's definitely to do with something over something instead of multiplying, instead of adding, instead of dividing, because you're dealing with equilibrium. So it's something on the right over something on the left. If you think about it, you can express the expression in terms of concentration, but for that, you know, 1 mark, you gotta be careful and also be creative in thinking about Kc bigger than 1. And you have 2 K-step value, so something over something that will give you bigger than 1, so that will be 1.26 times 10 to the 25 over 3.98 times 10 to the 20. If you can't see this happening, feel free to write the equation in terms of concentrations for Kc as a concentration of these, and you will see that they come to term with the K-step, which was related to the aqua complex, whereas in this thing you don't have the aqua complex anymore. The aqua complex is basically like intermediate species that was already existent from the very beginning. Press it into calculator and you will get this value, which you see is bigger than 1, and expected this equilibrium favors the right because it's the more stable complex. And that's it really for the 11 mark question. Question 5 is also on transition metal chemistry, but this is specifically on a cisplatin kind of chemistry. So they say use carboplatin and satraplatin as anti-cancer drug instead of cisplatin. So cisplatin is your case study. It has got 2 NH3 as well as 2 Cl, and it's a platinum 2 complex, and this is called cisplatin. And you know how cisplatin acts as an anti-cancer drug, and that is where they want you to describe the action of cisplatin as an anti-cancer drug. When you have DNA, you have this double helix or double-stranded helix, and it's a result of nitrogenous bases. If you do biology, you probably know about these. A, T, and G, C, these are the nitrogenous bases on the nucleotide backbone that forms the hydrogen bond and keep this structure intact because they're hydrogen bonded structure. And this is also the way that, you know, cancer cells will replicate. All right, so what happened is that cisplatin prevents the replication. So how it works is it prevents replication of cancerous cells. So your cells the cancerous cells are very dangerous because they multiply. If you can prevent them from multiplying by replicating themselves, then you can prevent the spread of cancer. So how does it work? You look at the NH3 molecule here. So the NH3 can come off and get replaced by the nitrogenous bases. So the NH3 ligands on cisplatin basically is a platinum Cl2 and NH3 twice, square bracket, without any charges because it's platinum 2, can be replaced or can be substituted. So it undergo a ligand substitution reaction by the nitrogenous bases. So those adenine, thymine, guanine, and cytosine on the DNA backbone, by the nitrogenous bases on the DNA backbone, therefore binding DNA onto platinum 2 complex. And if you do that, then your double helix replicate by opening up, and then it copy itself based on the complementary pairing, and then 2 strand will give you 4 strand, and 4 strand will be further divided. It's like keep on multiplying as if there are no tomorrow. Okay, so once you stop that replication, then there's no more DNA replication, cancerous cells stop replicating, and prevents cancer cells from spreading, so preventing cell replication. All right, so the second part of the question, so they want you to look at carboplatin complex. So that carboplatin complex, if you look at it carefully, it resembles that of cisplatin. So you have NH3 and NH3. So these two, they are a neutral molecule in the sense that neutral meaning neutral charge molecule because they have no charges. And then what you have is you have this thing. I don't know what I have done something wrong here. This should not be correct. Okay, so the 2 coming out towards you is bolded, and the 2 going away from you should be dashed like that. Okay, I've done something wrong there. So bolded like this, and then what you have is you have oxygen, so something there which I'm not going to draw, so I'm not exactly copying the question, but as you could see there, those are carboxylate. Okay, so I've not shown it completely, but this is a dicarboxylate anion, something you have done from ethane dioate acid, something similar to it. So meaning this one is a -1 charge, this thing is a -1 charge. And if that is true, then altogether that is still platinum 2. Platinum 2 really likes square planar geometry for a reason which I'll not go into detail here, but you can read up on the D8 chemistry of platinum, preferring square planar geometry instead of tetrahedral. So what I can say is it's a square planar preference in the carboplatin complex. In fact, you could see it in the way they draw the structure. So it says suggest, so you don't really even need to know this or this. The way they draw it is that 2 are coming out, 2 are going in. It's a square planar geometry instead of tetrahedral. If it is tetrahedral, they will have drawn something which is tetrahedral-like, where 2 are flat like this, and then 1 is coming out, 1 is going away from you. This will be tetrahedral. But the fact that they don't draw you 2 flat and 1 out and 1 in, meaning to say tetrahedral is not what they want. Okay, do I want to cross it like that? Maybe I want to cross it like this. Okay, so that it's clear that that's not what you want. So the next bit is suggest why carboplatin does not show cis and trans isomerism. So this is a cis position because they are 90 degrees from each other. But why does it not show trans isomerism when you could have trans isomer of cisplatin where the NH3 are 180 degrees from each other? So easily done with this because each of these is monodentate ligand, but this is a bidentate ligand, and when you have bidentate ligand, when you want to have trans geometry, it means you have to twist one of them to the other side such that they're separated by 180 degrees, and it depends on how long this backbone is. Look at the structure of carboplatin. You have quite a short backbone with just 1 carbon and a weird looking cyclobutane, which is a 4-membered square alkane, cyclic alkane to be exact. So what I can suggest is very short carbon chain in between So these are what we call spacer linker. So spacer linker because they are in between and they are just what we use to fill up the space. So very short of this spacer linker in between the two carboxylate end, and because they are too short, then how favorable is it to twist them apart? Not very favorable at all, and that is why we don't have trans isomer. So therefore these two oxygen atoms, ion with the minus charge, and the lone pair doesn't want to be 180 degree to each other because of the strand that it will create. So they cannot be 180 degree to each other. If they cannot be 180 degree to each other, therefore cannot have trans or does not have trans isomer as a result. Alright, so on to the next one, which is still not the last part of the question. So now you have satraplatin. Satraplatin is the one that is shown to the right of the question. So you will see that you have 2 times carboxylate. So I hope you can see that carboxylate are basically the oxygen like that. Let me show it. Platinum, or like this, and then or like this. So these two are carboxylate because it's actually all minus, because oxygen single bond is just like this. This is called a carboxylate. So you use the lone pair on the oxygen to form a bond there. So this is already -1, this is platinum 2. And don't forget that you also have the chlorine and chlorine, which is chlorine -1, chlorine -1. And then you have NH3, and then instead of me drawing the whole thing out, I have RNH2, where this is an amine. RNH2 is just the same as NH3, except you replace one of the H with R. So these two things there, the NH3 and the RNH2, have no charge. But you also have Cl- that have a -1 charge. You have 2 of them. You have 2 of these carboxylate. So they just want the charge, the oxidation state of the platinum. So it's a platinum +4 because that's the charge on the platinum ion center. And it's not the end of the question yet. The next part of the question, so the second bit, is actually something that looks like organic chemistry. So what we have is we have a benzene, we have a methyl benzene, 1,3 dimethyl benzene, because what you have is 1, 2, and 3 instead of 1, 2, 3, 4, 5. 1, 5 is bigger than 1, 3, so you always go for the lowest number. In that step 1, you get C8H6 or 4, and then you could turn that into acyl chloride like this. You could turn that into acyl chloride like this, and this M, this is 1,3 dimethyl benzene. So just a bit of naming there. So we could see that they've given us molecular formula, which is the actual number of atoms in that one single molecule there. So what I can say is that first of all, this is a CH3 and CH3. Now this is a COCl, so this has become acyl chloride. How about the molecular formula for this? I have 6 carbons, 7 and 8. So I have C8H. These are skeletal formula of benzene. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So C8H10 becomes C8H6O4. So you have lost hydrogen and you have gained oxygen. So we can be thinking about that in the context of organic chemistry. So that is definitely oxidation, especially in the context of organic chemistry. Oxidation of an alkyl side chain for benzene chemistry, however long your alkyl side chain is, oxidation of the alkyl side chain, L is going to be the benzoic acid, but not just benzoic acid, but it's going to be 1,3 benzodioic acid. So it's a 1,3 position, and it's a dioic acid, so it's not just benzoic acid. This is oxidation of the alkyl side chain of benzene as stated in the A2 syllabus. So in terms of reagent and condition, so step 1 is oxidation. This one can only work if you have acidified KMnO form. or you can say acidified MnO4 minus. Without the acid, it will not work and you have to reflux it. That is your oxidation reaction. In terms of going from here to here, this is your similar to your AS level conversion of hydroxyl into halogenoalkane. In A2, you learn converting carboxylic acid into acyl chloride, and you do that through the use of like SOCl2 or PCl5. And because you use SOCl2, you have to do at a room temperature because that reaction is very exothermic, and this thing can be easily turned to the acyl chloride just at room temperature alone. If you don't like SOCl2, you can do PCl3 and of course room temperature as well, because the same reaction, similar reaction, is going to be very exothermic, so you don't want it to be dangerous. Just a bit of a side note, so this is a side note which is not asked in this question, but in AS as well as A2, they like to ask you to write balance equation to show the conversion. So for example, in AS, I have an alcohol. If I do SOCl2, what I'll get is I'll get RCl because I convert the OH into Cl. And then what I'll get is the SOCl2 become SO2, one of the Cl combined with the H to give me HCl. In the context of these, I have two dicarboxylic acid. So I could have here, I could have done dicarboxylic acid, so meaning I would need 2 SOCl2 because I need to do it 2 times, and then I will get 2 acyl chloride, but I'll also get 2 SO2, but I also get 2 HCl because I'm doing it 2 times. If you use PCl3, you will get POCl3, and you will get PCl3, you will get RCl as well as POCl3 and HCl as well. If I'm not mistaken, you can try it. If I write ROH plus PCl3 RCl plus what is this? I think it works better if I use PCl5 because it's easier to balance the equation. RCl plus POCl3 plus HCl. So you could have done the same thing there, but with PCl5, and you will have one of the dicarboxylic, the diacyl chloride, and you get 2 POCl3 and 2 HCl. Okay, I better wrap this up before it gets messier. On to the next part of the question. So they do actually ask you to write the balance equation for these, which I already did. I was gonna show you just as out of interest, but they want you to write a balance equation so you could see it clearly like this. I'm going to convert it to molecular formula so that I don't have to draw this in my equation. So there's just C8 because 6 carbon, 7 and 8, and then there's 1, 2, 3, 4 hydrogen, 5 and 6 hydrogen, and there's 4 oxygen, 2 there, 2 on the left, 2 on the right, and then I could see that it's plus 2 SOCl2, then I'll get C8H4 because now it's just 4 hydrogen on the benzene ring, and I'll get O2 and Cl2, and don't forget, just like the equation I showed you above, hopefully it's nice and easy and straightforward like that. Onto the part 4 of this question. So they say in the first step, in the first reaction, the COCl2 reacts with AlCl3. They told you the question AlCl3 is a catalyst, and then they show you the second equation. So this reaction is the Friedel-Crafts acylation because you are introducing the acyl group and your electrophile is an acyl cation. So your this thing there is an acyl cation like this because you remove the Cl, one of the Cl, by reacting with AlCl3. Okay, so what is going on is this is reaction 1. If I just show you what happened in reaction 1, the AlCl3 reacts with one of the Cl of this acyl chloride, and what happened is you're gonna get AlCl4 minus, and then you're gonna get COCl a plus there. So in terms of charges, they balance out. This is a catalyst, and you will see how it reacts in reaction 2. Well, after reaction 2, it's gonna regenerate the catalyst. This is the mechanism that they want. So this is actually what they want for your answer, not this one. This is what they want for reaction 2. When I have the benzene, so they say C6H6, therefore I start from C6H6. I like to draw Cocoon structure whenever I do a mechanism involving benzene because it's easier for me to follow the electrons, but by all means you're more than welcome to use the ring if you want to. I mean, both versions will be correct, even though we know that Cocoon structure is not the universally accepted structure for benzene these days as a result of evidence from crystal structures among other data, but it's a lot easier to follow mechanism by thinking about the Cocoon structure. So that one will be the slow step. This is the rate determining step because you are breaking aromaticity. Anything that break the benzene ring stability is going to be slow. So the two other bonds remain where they are. This is where I have added the C double bond or Cl. So there's no more charge on the carbon because now it forms 4 bonds, 1, 2, 3, and 4. Just now it has 3 covalent bonds. I have my original hydrogen there. I have my original hydrogen there. This is now a carbocation. This is now a tetrahedral carbon with 1, 2, 3, and 4 covalent bonds and a carbon sp3. Alright. So the next part of the mechanism is basically returning the 2 electrons from the CH covalent bond. In doing so, this hydrogen will leave without any electrons, and that is why it's a minus H plus, because without any electrons, it gives you H plus. The 2 electrons go back to reforming the double bond of the aromatic ring. So this is going to be fast because you restore aromaticity. Fast because it will have low activation energy because you get back the stabilization. So that's why it's favored. So you get back the double bond, and now you have C or Cl. Now you have a H, but no more H there. But you will have to balance the equation with plus H plus. Remember just now that the AlCl4 minus is a catalyst. So they didn't ask you in this question, obviously, because that's the end of the question already. But as a side note, they could have asked, and I've seen this type of question before, explain why the AlCl3 is a catalyst. In the reaction 1, when you produce the electrophile, you also produce AlCl4 minus. At the end of this reaction, you kick out H plus. So that H plus can take away, well, in fact, it doesn't take away. It combined with the Cl minus, then you're going to regenerate AlCl3 and you will get HCl. And this is AlCl3 regenerated or reformed because it's a catalyst, and the catalyst is not used up in the reaction. It is simply involved in the reaction, and then at the end of the reaction, you get back the catalyst unreacted. So that's the end of that 12-mark question, just on, well, transition metals as well as on electrophilic substitution mechanism. Electrophilic substitution mechanism, in specifically the name of the reaction is called Friedel-Crafts acylation. On to the next question. So question 6. This is fumaric acid. So fumaric acid is a dicarboxylic acid. So it's also got an alkene. Alright, so identify the products when you react it with excess hot concentrated acidified KMnO4. You can imagine that when you oxidize it completely, so oxidative rupture of carbon-carbon double bond, just for that 1 mark, it's actually AS level concept. Alright, so this is going to give you HO2C, and then this is a R CH double bond. This is a R CH double bond because there's a H, and then there's a R group, and there's a carbon double bond. So it will be oxidized to give you that and that. So basically this is ethane dioic acid. In your A-level syllabus, in your A2 syllabus under carboxylic acid, you will see that ethane dioic acid can be oxidized, especially under this extreme condition where you have hot acidified KMnO4. This bit and this bit are symmetrical, so you just get the same ethane dioic acid. You will not get this as a final product, so this will not be your final product. Instead, they say identify the products. If you read the question, they say identify the products, is plural. So this is going to be your final product, CO2 and H2O. Okay, because this will be further oxidized, and then this will break and they will give you CO2 and H2O as stated in the syllabus, and also because ethane dioic acid is one of the few carboxylic acid that can be further oxidized. Now onto the next part of the question. This is about the polymer. This is about addition polymer first of all, because they say they want polyfumaric acid. So this is not going to be a condensation polymer to begin with. So if you have double bond there, double bond and double bond, so now it becomes single bond, and now you have the repeated chain. They want the repeat unit. They don't want 2 or 3 repeat unit. They just want the repeat unit. So on this carbon, I have CO2H and I have a H. So I have CO2H and I have a H. On the next carbon, I have CO2H and a H. Does it matter if I have one of them up there and one of them down there? Does not matter. This is now a single bond. Previously, you have a double bond, that prevent rotation about the double bond, and you could get cis and trans isomers that are different in 3-dimensional special arrangement. But here you have a single bond, because now this addition polymer, they just add and add and add, and what happened is this is single bond, which means you are free to rotate about single bond. So this is exactly the same as if the CO2H is down there, because you can rotate freely about single bond. The next one is when they want you to have condensation polymer, and they want you to draw ester bond fully displayed. So be very careful. In fact, you probably would know if you have done enough paper. This is ester bond fully displayed. Show all the bond. Okay, they don't say for the whole molecule, so we don't have to draw for the whole molecule. So ethane 1,2 diol, 1,2 like this, 2 carbon, ethane 1,2 diol, and then you gotta polymerize it with this alkene like this. And they want the repeat unit. So before I know what is the repeat unit, let me just draw out what is going on. The alcohol bit will lose the, well, in fact, the carboxylic acid bit will lose the OH, and this one will lose the H, this one will lose the OH, and this one will lose the H. So what happened then is you will get, I don't want to draw that N first. I want to draw O, and then C, double bond O, and I want to draw, how is it possible here? Perhaps it's probably easier if I just draw display. So there's going to be carbon double bond, so hydrogen. If you want, I can draw hydrogen. Nope, I should probably do the hydrogen down there as well, because I still have double bond. So this is trans, so I need to draw trans as well. What else can I do? I should probably do it a bit better. Let me draw trans a bit better. So if I have carbon double bond like this, I have hydrogen, I will have C double bond O. I show the carbon because ester bond fully display. Ester bond fully display. So this is C double bond O. This O here belongs to the alcohol. This O there belongs to the alcohol, because the acid loses the OH when they form ester. The alcohol loses the H when they form the ester. So that is going to give you like this, and then this alcohol bit will combine with the other bit there. So what I can say is that is one repeat unit from there to there. So that is one repeat unit. One repeat unit consisting of one ethane 1,2 diol unit, as well as one of the alkene with the dicarboxylic acid. If I draw another O here, there will be another part of the repeat unit already. So I should really stop there and say that is part of the repeat unit. This is still a trans, okay, because it started out with the trans isomer, which is the fumaric acid as shown there on the diagram, which is the trans isomer. So we haven't done addition polymerization, so it should still remain as trans, unlike the previous question where we did addition polymerization. So this question is quite tricky, yeah? On to the next part of the question. So they say why polyesters biodegrade, polyalkenes do not biodegrade easily. So polyalkenes contains basically the alkene are gone. You have no more carbon-carbon double bond. You just have single bond. So you can't do any reaction on it except to burn it, which is oxidation. Or what else can you do? But even then you can get a lot of toxic product, yeah. But polyester can be hydrolyzed, because if you have ester bond, you can break them down under acidic or basic condition. In fact, some of them could be catalyzed by bacteria as well, so presumably brought about by bacterial activity. So this is speculation, but in nature you have bacteria that can do that. So that is your biodegradability. On the other hand, polyalkenes have no more carbon-carbon double bond. Instead, they have many strong carbon-carbon single and also carbon-hydrogen bonds. Non-polar, so they are non-polar and therefore unreactive towards hydrolysis, so does not break down easily. Okay, in fact, the best way to just dispose of polyalkene is just most people just incinerate it, so basically just burn it. But having said that, they will release quite a lot of toxic materials depending on what is on the side chain of the addition polymer. Moving on to the next part of the question. So this is C. So they say fumaric acid. Fumaric acid just now was the trans isomer. What was it just now? CO2H and CO2H. Now you can react it with cold dilute acidified MnO4 minus. This is still oxidation, but this is mild oxidation, very mild oxidation of carbon-carbon double bond, and you will get diol, which is what they have shown you there. So CO2H like this, so you have lost a double bond, and now what you have done is you have just added OH and also OH across the double bond. They say only 3 stereoisomers of P exist, even though we have 2 chiral center there, carbon bonded to 4 different groups, 1, 2, 3, and there's a hydrogen. Same goes for this one, 1, 2, 3, and there's a hydrogen. So provided that you can rotate plane polarized light in opposite direction, so stereoisomers rotate plane polarized light in opposite direction. So this is something you have done in AS level chemistry. Okay, so the fact that you have 2 different combinations, so you can have this or this, what else, this and this. So clockwise, anti-clockwise, clockwise, and also anti-clockwise. So just like your head-tail combination in mathematics. Okay, so they want you to complete 3-dimensional diagram, so meaning you gotta have all those wedges and bolded lines to show the other 2 stereoisomers of P. So one of it has been shown for you, okay, but they tell you that out of these 4, only 3 are unique. Only 3 actually exist. Only 3 actually exist. And how do we know only 3 actually exist? That's because these and these are the same. And the reason why they are the same is because we can think about that this is symmetrical. You can see there's a plane of symmetry. So the product above has a plane of symmetry along the middle there. So because of this plane of symmetry, so plane of symmetry above in the molecule means we have mesoisomer. Mesoisomer is not really in your A-level syllabus. In fact, it's in many first-year undergraduate university syllabus as part of organic chemistry. But the fact that they're asking this question, you got to be thinking about what this actually means in terms of the 3-dimensional orientations. So they are the bolded as well as the dashed line. So one of them has been drawn for you. So if I just show it for you, just based on what have been given. So like that, and then they have the OH bolded and the OH bolded. Having said that, so the two OH are pointing towards you. When you're doing this kind of questions, avoid changing whatever is flat. Avoid changing whatever is flat, which is why they provided this for you. The flat one is not changing. The flat one, we don't want to change too many things at one time. And then they also provided for you the other two, and you are just supposed to fill them in like this, and the other one. So our question really is both of them in the same direction, in the way like this, and of course in the opposite direction where this one are flat, so I want them in the opposite direction. So here both are pointing out, so I want both are pointing in, both are pointing away. So both the OH are pointing away, so that's different definitely. And how about the other one? The other one would be when one is in and one is out. So just now I have put OH and OH pointing towards you, OH and OH pointing away from you. So I can choose really whichever one I want. I can choose like this. The OH is coming out, the OH is going in. And this is the one that we say are the same because of the presence of the plane of symmetry, that this and this side and this side is exactly the same. And you can rotate this molecule around. Then you actually have this thing called mesoisomer. These two are actually mesoisomers, so they are considered as one. So what we have is when it's clockwise, anti-clockwise, clockwise, they turn out to be the exact same thing, and therefore I have to put in the H there. So overall, there are just three isomers of it. You can convince yourself by drawing the other one where the OH is here and the OH is there, and then you can rotate the molecule around about the single bond, and you will see that they are the same molecule. This question is 2 marks only, so by right you're only supposed to be spending 2 minutes on it. So you should be able to come up with an idea on how to come up with the different combinations that are different. But this one with the OH are pointing away from you are definitely different from these, even though they look like you can twist them around. But remember, this is flat, so this flat one overlap with the flat one, but these two are pointing out, whereas these two are pointing in. So this and these are definitely different. That leave the other partner where they are not in the same direction, so which means they're trying to imply or suggest to you that clockwise, anti-clockwise, clockwise, basically one in and one out is considered the same as one out and one in. All right, so moving on to the next part of the question, which is question D. So this is on enzyme catalysis, and it's actually the end. It's a 3-mark question. It's the end of that 10-mark question. So what they want you to do, this is basically biological catalysis. It's one of the couple of rate of reaction essays or catalysis essays that are stated in the rate of reaction topic. So they said describe with the aid of a suitable label diagram. They give you some space, they give you some line. So avoid writing too much, but you do need to write some stuff by using the word describe, and you gotta have a diagram. So I'm not a very good artist, but I roughly know that they want me to think about enzyme. There's not a very well drawn enzyme, so I don't know how best to draw my enzyme. Let me think about it again. Okay, there's probably like E-shaped kind of thing, and then I have my substrate, which has to have similar kind of shape. So I can call that my substrate, and I can call that my enzyme. Okay, so when enzyme and substrate come together, then I will have an enzyme substrate complex. Let me see if I can make them come together. I should be able to if I just copy it and make it come together. Yes, I did. So what I could say now is this is enzyme substrate complex, and what will happen then is the enzyme will remain unchanged at the end of reaction because it's just acting as a biological catalyst. And what will happen with the products is, or what will happen with the substrate is, they will have been broken down into products, something like this. So it doesn't need to be the exact same diagram, but you should have been prepared for an essay like this. So you won't be shell shocked if this kind of thing come up. So that's your products, and they come from the substrate. And what happened with the enzyme is the enzyme remain unchanged at the end of reaction, remains unchanged. Okay, so that's the whole idea of enzymatic catalyzed reaction. In terms of your descriptions, I suppose you can say enzymes are biological catalysts. There's always a very powerful term to use, biological catalyst. Okay, so we need to talk about active site. So active site are basically where the substrate comes in and bind to the surface, and that's where the catalysis actually happen. So the use of the word active sites are associated with enzymes onto which substrate bind, substrate that have complementary shape. This is another term that's associated with biological catalyst. It needs to have the right shape or the right fit onto which substrate that have complementary shape or fit can bind onto. Alright, so what happened is they form the enzyme substrate complex. So the formation of the complex, the formation of the intermediate complex. So this last one is probably not necessary, but that's how you explain how catalysts in general lower the activation energy of a reaction by provides a new alternative reaction pathway. And it is this new alternative reaction pathway with a new lower activation energy that give rise to greater proportion of effective collisions. So greater proportion of effective collisions mean faster reaction. That is your classic explanation in AS rate of reaction. In this next question 7, so we have proline, which is a naturally occurring amino acid. So proline is quite unusual in the sense that if you have a look at this carbon here, let me just put it in this highlighted carbon pink there. So instead of bonded to NH2, it's actually bonded to NH because this NH is part of a ring structure. So that is how it's quite different to a normal amino acid where you have NH2 and CO2H, a H and an R group like this. That is how you would typically identify the fragment of an amino acid, but this is a special amino acid as a result of this, what we say, a secondary amine kind of linkage where you have a nitrogen bonded to one hydrogen and two carbon like this. So you have proline bonded to glycine, and you should know that glycine is where R is equal to H, because it's the simplest amino acid. It's one of the 22 that are not chiral, because when you have this as hydrogen and hydrogen, the carbon is not bonded to 4 different groups, so there will not be a chiral carbon in glycine, so glycine is not optically active. Since they want us to draw pro and gly, and they want us to fully display the peptide linkage, where the peptide linkage is basically the amide bond. So I'm going to draw proline first, but I do not need to show the peptide linkage. Well, I do not need to display for the proline. I can just draw them like this first of all. So that is the again, I've got to draw it from scratch. So that looks a bit better. So they want pro and gly. So I'm going to use this other bit from the gly, as well as this bit from the pro. So it's pro and gly to give me a dipeptide. So this is the carbon. I'm going to show the amide bond, which is the peptide bond. So I'm going to show it fully display on that side, but I'll use structure for the carboxylic acid. Don't forget, it's actually NH because I have not done any condensation reaction. On this bit or on this bit, I have simply condensed this bit and this bit, where I have actually lost, what have I lost? I have lost a OH and I have lost a H, such that I have a CO and an NH that give me the peptide linkage. They say you must fully display it. It doesn't hurt to actually say this is the peptide, where peptide is also known as amide linkage, but not every amide is peptide because not every amide is made out of amino acid. So be very careful about that. For that 2 marks, I don't think you can get it wrong if you want to score very well for paper 4. So the type of reaction is actually called condensation, as I mentioned just now. Condensation is not a new term. It was first encountered in O-level or IGCSE when you're doing 14 to 16 years old chemistry, where you have heard of condensation polymerization, where you kick out a lot of these small molecules. Here you kick out H and OH, you kick out water, and you condense the 2 molecules together. You also get condensation when you form ester. In the next part, so we have proline is able to form polyproline peptide chain. So they say about the secondary structure, and they say why the secondary structure cannot be stabilized by hydrogen bond. So hydrogen bonding is not possible, so that's what they are saying. So if you look at it, the hydrogen bonding is not possible. Well, I guess a very easy one is if you look at the polypropene chain. So I'm not going to draw the whole thing very well, but blah blah blah, and then that thing is CO, and then N, and then blah blah blah, and that thing is O, and so on and so forth like this. So hopefully you can see hydrogen bonding requires H bonded to F or N, and in this example your nitrogen does not have any hydrogen anymore. Which means that unlike this one where you still have the hydrogen bonded to the N because this was proglyne, now you have polyproline peptide chain. So what happened is the polyproline peptide chain. So this is the AS level question, by the way, because it's about what is hydrogen bond. So that chain contains no hydrogen atom bonded to highly electronegative element, nitrogen, oxygen, or fluorine, which of course is not available in this case, but you got oxygen and nitrogen, and none of them contains hydrogen bonded to itself. So therefore, no hydrogen bond is possible, just for that 1 mark, which is a suggestive kind of question. On to the next part, which is part B. So we have a couple of reaction scheme. We can hopefully see that in reaction 1 is a reaction with NaOH, and what we have is if I just draw out the skeletal formula, which is this, and you can hopefully see that this is your carboxylic acid group that's acidic, and this is your basic group because the nitrogen has got a lone pair, which they haven't shown you very conveniently. And when you react it with NaOH, this is a base. The base is going to react with the acid because it's not condensation reaction, so you don't lose the OH. It's acid-base neutralization reaction. They want you to write an equation. So they have given you proline as C4N7, NHCO2H. So they purposely show you the CO2H like this. You only have one CO2H. So the C4N7 thing is, well, C4H7, sorry, not N7. There's always a problem when you copy from somewhere that you might miss something. But anyway, the amine group doesn't do anything because there's a base and this is the base. And the CO2H becomes CO2 minus because it becomes CO or minus after you lose the H plus, and now it becomes a salt. And what happened then is the H plus combined with the OH minus to give you H2O. The Na plus come from the sodium hydroxide. So I always enjoy, or I always like to write my salt in this form of ionic structure, where a lot of books will ignore the sign of the charges. It's not wrong, it's just that I like to see what I'm writing so that it's much clearer to me. But that's just me, alright? in the next part, I have a secondary amine functional group. That was what we said about proline. So what happened then is they give us dimethylamine reacts with acyl chloride like that. So what we could see is this is the example given. So if I just draw the skeletal formula, they said that reacts with this thing called acyl chloride. Acyl chloride has looks like carboxylic acid, but the OH of the carboxylic acid has been replaced by a halogen Cl in this case. So what happened then is it's going to undergo a condensation reaction, and you will kick out a Cl and a H. So it's still called a condensation reaction because you still condense two molecules together to give you an ester. Sorry, not ester. I beg your pardon of my game today. So this is an amide. This is not a peptide because these are not amino acid residue. And what happened is you kick out a small molecule called HCl. So in the question, the product of reaction 2, if I have my proline, for example, let me just take that. So I'll just copy it. So this is what we want. Previously was about acid and base reaction. When you react with acyl chloride, it's not an acid-base reaction. Instead, it's a condensation reaction. So we don't care so much about acid or base properties anymore. And which one will it react with acyl chloride? First of all, this is amine. The amine is the nucleophile. So I can just circle that. So this is the nucleophile. And this is the electrophile due to the two highly electron withdrawing groups. So it's the amine that it will react to give you the amide. So this will be R, and what happened then is you will get the carboxylic acid remaining, and you will have kicked out the H and the Cl. So if I just say like this and like this, that means you will get HCl as your other product. But they say they just want R, so you know we don't care so much about the HCl. So this must be what is this? RCOCl. Oops, sorry, they actually gave you CH3 COCl, so CH3 COCl, so you will get CH3Cl there, and this must be product R, where they give you the molecular formula. Let's just check our carbon. 1, 2, 3, 4, 5, 6, 7. So there's 7 carbon. Let's just check our hydrogen. So there's 1 hydrogen because carbon form 4 covalent bond. So there's 1 hydrogen there because the other thing are bonded to something that are shown already. 1 hydrogen, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have H11 and I have 1 nitrogen here. I have 3 oxygen, so it's NO3, and this is the product R as intended, and they want you to suggest the skeletal formula. So this is the skeletal formula you want. If I just put this in a square bracket, yep, that looks perfect. So that is exactly what we want. We want skeletal formula, so any other thing will not be accepted. For your part 3, we're trying to do reaction 3, where hopefully you can see that the carboxylic acid has gone to a primary alcohol. So my diagrams are getting worse and worse. It's very inconvenient when you don't have the paper in front of you. So as someone has told me that I am putting in double the effort, and in fact I'm putting double the effort to actually do these kind of tutorials without the question paper in front of me. Now this carbon with the OH is bonded to one other carbon, and as a result of it, it's got 2 hydrogen bonded to it. This is a primary alcohol. Whereas previously it was a carboxylic acid. Well, not the whole thing. This is still NH. So this thing is carboxylic acid. So this is very clearly a reduction. This is the type of reaction. But the question is not asking on the type of reaction. It's asking you for the reagent. So to do reduction, we need a reducing agent. So we can use LiAlH4, the name of which is lithium aluminium hydride, and it's pretty sensitive to water. So we use it in dry ether. Ether is a solvent which doesn't contain water because I use dry ether. In the next part of the question, part C, so it's a stepwise process. So they're saying that we are using a multi-stage route in order to react with that ester and alkene, and I get blah 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 blah. So you can see name all, so they want name, there's the first thing, and they want all, there's the second thing. So do not miss anything, even the simplest thing of all. CH2, CO2, C2H5 so what does this look like? So this looks like COO, C2H5, so 2 carbon, 1 2, C2H5, CO2, and then I got CH2 there, so CO or like this. Okay, so this is my CH2 in between. So what functional group do I have? Well, very clearly I have an ester functional group. Hope you can see the ester. This is the ester functional group, and the rest of it is just alkane chemistry, so it's just alkane. Actually, I meant to write the ester in pink, and I meant to write the alkane in green. Not that it matters, you'll be writing in black or blue ink anyway in the real exam. That's the first bit. How about the second bit? CH2, CHCN. So if I just draw skeletal, because it's a good practice to practice skeletal, we can see that this is what you call nitrile. Nitrile is an AS functional group, and you also have another functional group which is alkene, carbon-carbon double bond. It's an O-level IGCSE kind of functional group, I guess. I think that's it really. So it's just alkene and nitrile chemistry, because the hydrogen is bonded to alkene, hydrogen is bonded to the alkene there. Okay, so what type of reactions occur in stage 1? So you have two things come together and give you one thing, so you get one product. So it's not a condensation, so because condensation will kick out a small molecule, whereas two things come together to give you lesser than two things. This is an example of an addition reaction. So the type of reaction is simply called addition reaction. This is in AS syllabus under type of reaction. So the next part of the question, so they are saying that in stage 2, if I just draw out part of the molecule U, so CO2, C2H5, I also have the exact same group there, CO2, C2H5. Both of these are ester, as you could see, the COO or the CO2 and then alkyl group. If I just draw with another color on the other side, there's just CH. If I choose another color, there's CH2, CH2CN. So this thing here, this is nitrile, and I hope you can see that if I choose a different color for the arrow, I'm moving back and forth between the other different colors. This is the ester and this is the ester, so that and that is the ester functional group, and this is reagent V, this is U, and then I go to W. What they show as W is that is CO2, C2H5. So nothing has changed on the ester. So the ester hasn't reacted. The ester is still the same. Ester still around. The H is still around. But what is different now is the CH2 is now CH2NH2. In every single type of reaction, so what we do is we focus on what has changed and what is different. So this is now different, and this is the one, well, actually that was the same. What has changed means what is different, right? So what has happened is nitrile has gone to amine. This is a amine, R and H2. This is a primary amine because the NH2 is bonded to one other carbon. You can say the amine has two hydrogen on the nitrogen. It's the same idea. So for this part 3, when they want suitable reagent V, so this is a reduction of nitrile. You cannot say hydrolysis of nitrile because you do not get carboxylic acid. And also if you use acidic condition to get the nitrile into carboxylic acid, they would have hydrolyzed the ester into carboxylic acid as well. Whereas here you can see the ester remains unhydrolyzed, and because this is not hydrolysis of amine, this is the reduction of amine. So I will also use LiAlH4 in dry ether, just like one of our earlier questions on the reduction of a carboxylic acid. There is an alternative to this answer, where in the A2 syllabus you will have learned that you can reduce nitrile whether using LiAlH4 or you can use H2 and nickel catalyst, and that would only happen at high pressure, for instance, to for the rate of reactions and also forcing through the reaction. The next part of the question, so this is a multi-step reaction, remember? So in stage 3, what we have is we have this ester, and now we also have the ester on the other side and the H, and what happened is CH2, CH2, CH2 and NH2, they form a cyclic chain, well, not really a chain, but a cyclic compound, where it looks like this. Hope you can see that one of the esters is still around. Okay, we are not sure which ester it is, but there are two of that ester, one of them is still around. And you could hopefully see that this is the nitrogen with the lone pair, so this is the rich in electron, and this is going to be the nucleophile. They haven't asked a mechanism here. Yeah, they haven't asked a mechanism here, but I could see that in the next part there's a mechanism question, which is kind of related to this question actually. But if you follow through the number of carbon, if I say this is not carbon, but if I just say this is atom number 1, 2, 3, and 4. So there's atom number 1, 2, 3, and 4, and there's my number 5. Okay, so one of these ester carbon is going to be carbon number 6. So it could be this carbon or it could be this carbon, it doesn't matter. But if it is this carbon, then this becomes the ester. If it is this carbon, then this becomes the side chain ester. Alright, so that's what happened really. So it must have attacked, this nucleophile must have attacked one of these electrophilic carbon of the ester. And in this kind of attack, you are forming an amide. This is called an amide linkage. And forming an amide linkage is actually part of AS condensation reaction. So the type of reaction is going to be condensation. A lot of this whole question has been about condensation reaction. But at the same time, they also say you kick out Y, because if you add onto this carbon number 6, all right, so if I say there's carbon number 6, if I use a different color, pink color one, that means I have lost the rest of the molecule, and I will have lost one of the hydrogen. You will hopefully see one of the hydrogen is gone, as well as all this C2H5O, because it's just a C double bond O from one of these ester linkages. So what we have really, Y is going to be, it has C2H5, it has an O, but it also has a H from the hydrogen. So I imagine that you can also call, instead of condensation, because you do actually form amide linkage, potentially you could call this elimination, because one reactant give you two products. That is characteristic of elimination reaction. As defined in AS, you end up with more things than what you started with. That is how you characterize elimination. And as what I explained before, this C2H5OH is going to be one of the side product, which is going to be the Y being kicked out. They said deduce the identity, so you could have given the formula like that, or you could have given the name. There's just ethanol. In fact, you could also give CH3, CH2OH, because all three of these are the identity of Y as the product given out. In the next question, so this is about mechanism. This looks tricky. So they say they have given you the starting material, which is this one. Nope, not that. So CO2H like this, and they show the CO like that, and they have the NH2 like that. They purposely left the middle one empty, and they show you the final product, which is the proline. And proline has got that nitrogen there, NH, and COOH. So of course they show you CO2H. I've just decided to draw the skeleton like this. Doesn't matter. The fact that they show you this and this means it's a two-step thing. Step 1, I'm going to show using a blue color, something else, which is not given. So step 2, step 1 and step 2. I don't know why I wrote Roman numeral. Step 1 and step 2. As you could see, they want you to draw the structure of any organic intermediate. When I see that particular term, it reminds me straight away that it's not a transition state, it's an intermediate ion. That's what they want me to do based on the question. Draw the structure of any organic intermediate ion. On my mind, I should be thinking about SN1 reaction and not SN2, because I am guided by what the information given in the question like that. In SN1, it's a two-step mechanism, step 1 and step 2. So the first step is the slow step. It's the slow step because it's the rate determining step, which is defined the slowest step in the overall reaction. Since they have given me skeletal formula, I'm going to maintain it like a skeletal formula like this. This is actually not a secondary carbocation, but well, it is actually a secondary carbocation. I haven't shown the H there, but I'm just showing the H there even though we don't usually show it for skeletal formula. Hopefully you can see this is a trigonal planar carbon with 1, 2, and 3 bond pair and 0 lone pair, because with the 4 valence electron carbon, now you have +1, you have 3 valence electrons on the carbon. They are all used for bonding. Trigonal planar 120-degree carbon sp2 hybridized. This lone pair on the nitrogen is freely available. Rich attack pool from the lone pair attacks the fully positive carbocation. This is, by the way, a secondary carbocation, intermediate, because the carbon with the positive charge is bonded to 1 and 2 other carbon. This is going to be the fast step, because this was already the slow step. The first step in the SN1 mechanism proceed via slow step. Alright, so they do ask you to draw curly arrows, ions, partial charges, lone pairs. So I should have an ion at some point, alright, as appropriate. And this question has been really long so far. Now they want you to identify the chiral center in this proline. Hopefully you can read skeletal formula. This is a CH2 because carbon form 4 bond. A CH2 cannot be chiral. This is nitrogen, so it's not chiral on the carbon. This is a CO2H, is sp2 carbon with a carbonyl bond there, so it's not chiral. Hopefully you can see the chiral carbon is going to be there. They want you to identify with an asterisk. They don't want a circle, they don't want a dash or whatever. This carbon is bonded to 1 nitrogen, 1 carbon there, another carbon which is different from that carbon, and there's a hydrogen because carbon form 4 bonds. Alright, now I'm a bit scared to the last part of the question because I don't want to have to draw the whole thing out, but it looks like I might have no choice in order to go through this question. So let me take my time and draw it. Actually, do I want to take my time and draw it? Yeah, why not? The whole idea of not being able to show the question paper is really frustrating. But here I am, venting out my frustration and not being able to show the paper at all. But what can I do, right? These are rules, and rules have to be followed. Blah 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 blah. I'm not interested in the other one. CONHCH. Okay, I'm getting tired. I'm not gonna draw the whole thing out. Blah 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 blah. Okay. Anyway, so what I can say is I can hopefully see that this is one part of an amino acid. So this is your number 1. I'm gonna do a simple exercise where I'll show you a couple, and then you can do the rest on your own. If I use a different color. So this is different because this is a CH and a CH3, this is a CH and a H. So you look for the R group. Is the R group different? And I'm talking about the R group of an amino acid where you have Cr and then H and then NH2 and CO2H. This is an amino acid residue. Well, amino acid essentially, not residue. So these are polypeptides, so you gotta look for whatever you're looking for. And hopefully you can see that this thing actually ends there, because the end of a proline is a secondary amine. It does not have a hydrogen when it forms polypeptide. So there's just another one, it's different. And on to the next one. This is definitely different then, because this is part of a long chain. So I'm running out of color actually. Red color, for example. So there's my number 4. You can hopefully see blah 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 blah. So by the way, you can hopefully see that this is also the green color one. So this is the same amino acid as 2, but read question. What does the question want? the question specifically say number of amino acid units. Of course, the structure shown here is incomplete. I leave it to you to find the rest of it. And from your diagram, from what I have told you, you should be able to work out for the rest of it. And you are not trying to find how many different amino acid. You are trying to find number of amino acid units in the structure shown. So altogether, I actually got a total of 9 amino acids units. Of course, in terms of difference, you can already see that different amino acid, these and these are the same amino acid. So if the question is changed slightly to how many different amino acid units, then you need to take into account that these and these are the same and you don't miscount them. I put in the same number here because I just want to raise out the issue that these are the same amino acid, but I also highlighted the point that the question asks you specifically number of amino acid units and not number of different amino acid units. Alright, so be very, very careful about that. In the next part of the question, so what do we have? They say at pH 6.5, proline is a Zwitter ion. So Zwitter ion meaning that exists as the positive and a negative charge format. So the first bit is draw the structure of the Zwitter ion. So I am just going to draw that. Not very well drawn one, so let me try that again. Much better. So that would be your carboxylic acid, and this would be your NH like that. This is your Zwitter ion, but the exists as, sorry, this is not your Zwitter ion, this is proline molecule. When the exists as Zwitter ion, this will be O minus, and this other one will be protonated. It will become NH2 plus, where the nitrogen form 1, 2, and then 2 other bond to 2 other hydrogen, giving you a positive charge on the nitrogen. That's why it's called Zwitter ion. All right. The next part of the question is basically asking you, explain how Zwitter ion of proline forms. So basically, how do you get Zwitter ion? You get a transfer of protons. This is your proton from the carboxylic group, the carboxylic acid, which is acidic, to the basic amine group of the amino acids. Therefore, both centers now have charges, but net charge meaning the overall charge of the species remains 0. Okay, so usually these kind of questions are linked to electrophoresis, and the next part of the question is actually asking you a little bit about electrophoresis, but before that, they say about this thing called isoelectric point. So the isoelectric point of an amino acid is the pH at which it exists as Zwitter ion, So you know the counter net charge is counted by the same charges on both the acidic group and the basic group, such that they remain overall net charge is 0. Okay, so if lesser than this isoelectric point, we can think about being acidic environment. So therefore, your basic NH2 will protonate. On the other hand, if I have greater than the isoelectric point, what I'll have like a basic situation where I'll have the acidic CO2H group will deprotonate, because acid react with bases, bases react with acid. Now to the 3 things there. So they told you the isoelectric point is 6.5. And then they are telling you at pH 4.0, isn't it? Earlier in the question, if you read E part 1, at pH 6.5, proline is Zwitter ions. Let me have a look. Oh no, these are just information. Sorry, I was jumping straight onto the next one. So if I just draw the three thing first, like this. So this isoelectric point is 6.5, and then I have NH2, CO2H, and there's 6.0, and last but not least, this glutamic acid is 3.1 there as the isoelectric point. So a mixture of these amino acids you analyze by this technique called electrophoresis. So you apply electric field, electric gradient using a buffer. So you need a buffer solution. Your buffer is at pH 4.0. That is what we are comparing these against the buffer pH. So this isoelectric point is the buffer pH is lower than the isoelectric point. So this is going to be the acidic environment. So at pH 4.0, therefore at pH 4.0, so your pH currently is lesser than isoelectric point, so this is going to be acidic compared to that. So the basic group will not remain as NH like this. Instead, what they'll do is they will protonate, but your acidic group will remain acidic. Okay, now at pH 4.0, it is still lesser than 6.0, so again it is your alkaline or your basic group. They will protonate while your acidic group remains the same there. Onto pH 4.0, now this is 3.1. This is lesser than this buffer pH, so what will happen is it will deprotonate at 4.0 because this pH is higher than the isoelectric point. So it will not protonate there. It's in a basic environment because pH 4.0 is greater than the 3.1, which is the isoelectric point for this acid. So you are essentially in a basic environment. And when in a basic environment, your base will remain as basic, but your acid will not remain like that. Instead, they will be deprotonated and they will give you a -2 overall charge. So that is my overall takeaway message, my net charge. My net charge at pH 4.0, pH 4.0, this is from the buffer, is going to be the sum of that net charges, I guess, +1 for the overall species, +1, and this one is going to be -2 for the overall species. As a result of that, I can see that these two and this is going to be moving in the opposite direction. So they want you to draw and label 3 spots on this electrogram. So I wonder if I can draw a perfect. Yep, that's perfect. I have a plus, I have a minus. I have this thing there and I have this thing there, which I don't allow them to go all the way there. Roughly in the middle is that mixture being applied here. So remember here, you do not have a polypeptide, a dipeptide, or tripeptide. Instead, you just have the 3 amino acids. Alright? If your net charges is negative, it will be attracted towards the positive. These are positive, they'll be attracted towards the negative. But as you could see that this is quite a simple side chain. Well, it's not a simple side chain, whereas this side chain is much bulkier than this. Much bulkier side chain. If I can just kind of show that thing there. So much bulkier or heavier side chain or bigger side chain. So therefore it travels slower. Therefore travels lesser, travels slower. So over the same period of time, so that thing is not going to be as far. The other thing will travel further. But of course, both of these are +1, which means the +2, perhaps I can make it more dramatic. The +2 is going to be way more than the +1, so it's about here for the -1. So +2 I can say is probably around there. Just give and take, it's an estimate, right? So this is a -2, it's going to be more attracted towards there. Even though it's much bigger side chain, however, the charge makes it more attracted towards them. Maybe not as dramatic. Anyway, I'm just being over dramatic here. So what happened with these is, this must be the glutamic acid, the one with the -2 charge, because -2 is attracted towards the plus. Between the two pluses, the plus net charge which are attracted towards the anion. The one that is less bulky will travel a bit further. So this middle one is the alanine, whatever you call it. So alanine is going to travel just a bit further compared to proline. So proline doesn't travel as far. It does the explanation, so I've just explained the whole thing just now. So let's see if we can explain it. So this is part 2, electrophoresis questions. Quite a lot of lines for that format. I guess the first thing I should say is at pH 4.0, proline and alanine have both amine group protonated as pH 4.0 greater than their isoelectric point, something you have learned from well, I guess the syllabus, all right, from this part of the curriculum. So therefore have net +1 charge. Okay, so that's my point number 1. For glutamic acid, so pH 4.0 is lesser than isoelectric point. I can write down the value, which was 3.1. So the carboxylic acid get deprotonated, and when I get deprotonated, I get net charges of -2 because I have 2 carboxylic acid group in glutamic acid, one from the main amino acid backbones and one from the side chain. So overall, I guess I could use a different color just to prove my point. Overall, -2 charge species move in opposite direction to that of +1 charge species. -2 move further towards positive terminal. Okay, and in terms of the +1 and +1s, so between the two +1 charge species, I can say that the alanine has a simpler or smaller or less heavier side group or side chain. Therefore, alanine spot travel further. Alanine travels further than proline. They are both +1, so they travel further towards the negative terminal. Now, do we need to write that much? Well, how much you write really depends on how much you want to score these 4 marks. I guess you probably get draw and label 3 spot. That's probably 2 marks. In terms of the explanation, it's probably worth another 2 or 3 marks. I have no idea how these marks are distributed. In an exam, you really just have to explain your ideas. If you are able to work out what it was, you should be able to express the idea easily. Okay, these are the wordy part of the exam. I remember doing this calculation for the next part of the questions. It's actually the last question. So this paper is quite a very challenging paper 4 actually, and this was probably the paper that actually landed me in problem with the copyright issues and stuff. But anyway, that's beyond me now, so I put that behind me, and going forward I'll just do paper tutorials where I don't show the question paper. Hope that's not a problem at all. I'm not telling you where to get question paper. You can get your own question paper because you're more resourceful than me, so I guess that's alright. So now this is ACES, ACES. The anion is a strong base. So the anion meaning to say, I guess if I draw the whole thing, copy and then paste. So this is the anion where I remove one of the H. So it's just like sulfuric acid, but except that there's the anion, so that is a strong base. It really wants to protonate something. Now this is how you prepare the buffer solution. You get blah 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 blah, all that information. So what can I say from this information? I want the pH of the buffer. So first of all, I will get the mole of the salt, and the salt that I have is going to be C4H9N2O4 S minus Na plus. That is what they are telling us, and that is actually a strong base because it's combined with the Na plus. It's a strong base. This is a strong base. Alright, it reacts with HCl in a 1-to-1 ratio. That's what they tell you. Reacts with HCl in a 1-to-1 mole ratio. So it's a strong base. It will react with acid. So the mole of the salt. I wonder if I can change the color of the ink. Now red is too bad. If I change it to purple. So the mole of the salt is going to be mass over mR. I started with 3.50 gram of the salt, and I can work out the mR of the salt. Actually, I don't need to work out. This was given in the question. The mR of the salt, the sodium salt, is 204.1. Put that in and you will get 0.01715 mole. This is in gram. This is in gram per mole. So you know, they will definitely give you mole because it's mass over mR. On to the next part of the working. How much HCl did I add altogether? In the question, you say you added 50 cm cubed, so 50 times 10 to the minus 3 to convert that to dm cubed, multiply by the concentration in mole per dm cubed, and I get 0.01 mole. By right, given the accuracy of the data, 1, 2, 3, 1, 2, 3, I should really express my answer to 3 significant figure, 1, 2, 3, just to be consistent and appropriate with my number of significant figure. Now they're telling me that the salt itself, so acids which are very, very strong base, that's what they're telling me. Well, in fact, that's what they have told me in the question. So they will give me this acid, so SH, and then I'll get NaCl. So this is a strong base, this is the salt, and then this is acid. So strong base will accept the protons, and then you will get this weak acid. Alright, and you get this another salt. Doesn't matter, it just protonate, accept the H. This is a weak acid, and this is your acids. If you look at the question, acids has pKa, so the pKa of acids is 6.88 at 298 Kelvin. So acids is a weak acid. No questions asked because you talk about pKa because it's a weak acid. What do we know? We know that they react in a 1-to-1 mole ratio. So therefore we can see that the salt of acids is in excess. So all the HCl will have reacted, because if this and this react in a 1-to-1 mole ratio, let me just get that straight, 0.01715. So if we can see that 1 mole reacts with 1 mole, but here 0.01 mole should react with 0.01 mole. So the salt is in excess. So the salt which is this one, okay, which is salt of acids is in excess. HCl is used up. HCl is strong acid. Alright, so the salt is still around, but you are also producing the weak acid. So just because the strong acid is used up, you also produce the weak acid as this reaction progresses. The weak acid and the salt of the weak acid is present. This is going to give you an acidic buffer. Alright, so therefore the mole of the salt in excess, how much of the salt is present in excess? So how much of this is present in excess? Well, how much did you add in altogether? You add in this much. If you have this much HCl, they react in 1-to-1, so 0.01 mole will react. Only 0.0100 mole of the salt reacted. So since that's the case, so there's 0.01715 from up here. Take away however much they reacted, so minus 0.0100, and I will get 7.15 times 10 to the minus 3 mole. This is the mole of the salt in excess, but what is the mole of the acid, the weak acid? So now the mole of the excess, which is the weak acid present. Well, from the balance equations, you get 1 mole of the weak acid from 1 mole of the HCl that fully reacted. This one fully reacted. If you have 1 mole of these fully reacted, you get 1 mole of these. So I know 0.0100 mole of HCl fully reacted, so I'll get 0.0100 mole of the weak acid excess. It's going to be equal to the mole of HCl fully reacted, and that is equal to 0.0100 mole. So what do we have in the next part is our buffer equation. So in our next part is just what we have is we have our weak acid, which I can label HX. So this is your excess, which give you H plus and the X minus conjugate base. You also have the salt of the weak acid, which is your the salt itself is Na plus and X minus. This one fully dissolved, all sodium salt dissolved in water, then you get Na plus plus X minus. Hope you can see that as a result of these and these, since this is in equilibrium and this is fully dissociated, so the mole of X minus at equilibrium is going to be roughly equal to the X minus from the salt. By right, it should be however much of these and these combined together, because these are not individual, these are in the same solution mixture. You have some bit of the weak acid produced in the reaction, but you also have the salt of the weak acid present in excess. So you have an acidic buffer, which is a mixture of these two. In equilibrium, how much of X minus you have is going to come predominantly from the salt rather than from the equilibrium. This gives rise to your buffer equation. So Ka is going to be for the weak acid, not for the full equation like that. So for the weak acid, it looks like this. Then you do approximation. Then this is going to be H plus X minus from the salt. And then you assume that the weak acid dissociate very little, that the concentration is similar to its original concentration. So what do we have there? I can just see that this is the same as Ka, H plus, and then I have the salt of excess divided by the weak acid itself, which is the excess. Now we know pKa of excess was given as 6.88, so minus log 10 of Ka is 6.88. Ka is 10 to the power minus 6.88. This is Ka, and I could have Ka. What is H plus then? H plus is Ka times excess over the salt of excess like this. So I could have cut down this step really, because I do have this previous step already. So I can just move this up here. What else do I have? If I just put in my value now, so my Ka is 10 to the power minus 6.88. My concentration of excess is the weak acid. So the mole of the weak acid is 0.0100. That is mole. So I'm going to put in 0.0100 mole. I have a total volume. This is going to give me mole per dm cube to give me concentration. I don't care about volume yet, because what I could do in the next step is I'm going to have the exact same volume for the salt of the excess, because these and these are in the same solution mixture. They have the same total volume. So the next part is the salt of the excess present in excess is 7.15 times 10 to the minus 3. That was mole, and this is divided by the same volume total as the other excess, because they are in the same solution mixture. This was why the total volume does not need to be known. and you could pop that into a calculator, and you could get H plus as 1.8437 times 10 to the minus 7. This is concentration in mole per dm cube. Last but not least, they want the pH, which is minus log 10 of H plus. I pop that in, I get 6.734. I can run it up to 3 significant figure as per the rest of my data. The rest of my data was rounded to 3 significant figure because the original data given was all to 3 significant figure. This is called appropriate number of significant figure as per the data given. Alright, this has been a really long tutorial for this paper form. Don't know how helpful these things are without the actual question paper, but do let me know in the comment section how you feel about this kind of tutorial. And does take me quite a while, a little great deal more effort than having the question paper shown in front of me, in front of you. But yeah, cheers for the support, and please share the channel widely with all your friends, chat group, juniors, seniors from school, your teachers, whoever else you think these kind of tutorials might be helpful for. My time is pretty limited these days, so I'm limiting myself to just one full tutorial a week, and I wouldn't do a paper for every single week. It does take a lot of time, time of which I can't dedicate anymore, unlike this time last year where I was free-flowing with time. But I'm a little bit less generous with time these days because of the work-life balance and stuff. Alright, thank you for watching, and follow me at ptet.chemistry. There's ptet.chemistry on Facebook, Instagram, and Twitter to get connected, and leave comments on the video, leave likes, and let me know how things are on your other end. Alright, thank you for watching. See you in the next tutorial video.